There's a photograph sitting in a NASA archive right now that could rewrite everything we thought we knew about what travels between the stars. It shows something that shouldn't exist, captured by a rover on Mars during a moment when the universe decided to reveal one of its most carefully guarded secrets. On October 3rd, just hours ago, an object designated 3I Atlas made its closest approach to Mars. 29 million kilometers separated the red planet from something that had traveled across the void between solar systems to arrive at our cosmic doorstep, with timing so precise it borders on impossible. What happened next changed everything. A faint blue anomaly appeared in stacked images from the Perseverance rover, glowing against the Martian night at the exact coordinates where 3I Atlas was predicted to pass. But here's the problem. Every space-based telescope tracking this object showed carbon dioxide chemistry and neutral to greenish colors. Blue doesn't fit. Blue suggests something with reflective properties that aren't found in natural comets. This isn't just another space rock drifting through our solar system. This is the third confirmed interstellar visitor we've detected, and it's breaking every rule we thought governed objects from beyond our stellar neighborhood. Tonight, we're diving deep into what might be the most important astronomical discovery of our lifetime. Because what these new images from Mars reveal isn't just strange, it's impossible according to everything we understand about interstellar objects. And the implications of what we're seeing could force us to confront a reality that challenges our most fundamental assumptions about our place in the universe. If you're ready to explore the evidence that's dividing the scientific community and discover why some researchers are whispering about possibilities that would have been dismissed as science fiction just months ago, then buckle up. Because by the end of this investigation, you'll understand why this blue smudge from Mars might be the crack in our understanding that changes everything we thought we knew about what moves between the stars. Part 1. The visitor that defied all expectations. 3 months ago, automated telescopes scanning the southern sky detected something extraordinary. Moving against the stellar background at nearly 3 arc-seconds per hour, faster than any asteroid should move at that distance, was an object following a trajectory that could only mean one thing. This visitor came from another star system entirely. The discovery triggered immediate follow-up observations from major observatories worldwide. Within hours, confirmation arrived from multiple sites. The object was real, it was fast, and its trajectory was mathematically impossible for any natural solar system inhabitant. They designated it 3I Atlas, marking it as the third confirmed interstellar object, following ʻOumuamua in 2017 and Borisov in 2019. But 3I Atlas was different from its predecessors in ways that would soon become deeply unsettling. The speed alone should have been our first warning. 130,000 miles per hour. That's not just fast by earthly standards. That's the fastest solar system visitor we've ever recorded. To put this in perspective, imagine a bullet traveling at typical velocity, then multiply that speed by 170. That's 3I Atlas screaming through space with the momentum of an entirely different star system. But velocity was only the beginning of its mysteries. Within days of discovery, telescopes revealed something that challenged every expectation of what an interstellar rock should look like. Surrounding the invisible nucleus was a fuzzy, compact coma, a cloud of dust and gas being actively released by solar heating. This wasn't some cold, dead fragment of interstellar debris. This thing was alive, breathing vapor into space as our sun's energy awakened dormant materials that had slumbered for potentially millions of years in the cold between the stars. The implications struck the astronomical community like a meteor impact. Here was an object that had traveled the galactic wilderness, surviving radiation that would sterilize any earthly organism, enduring temperatures just degrees above absolute zero. Yet the moment our sun's warmth touched it, it began to transform, creating a ghostly atmosphere in the vacuum of space. NASA immediately marshaled its most powerful instruments: the Hubble Space Telescope, the James Webb Space Telescope, The Swift Observatory and dozens of ground-based facilities turned their attention toward this cosmic messenger. This wasn't just another comet to catalogue. This was carrying chemical signatures that could reveal conditions in an alien planetary nursery billions of years old. But as the world's most advanced telescopes began their systematic study, a troubling pattern emerged. Every observation seemed to raise more questions than it answered. The object's behavior matched no existing model of interstellar debris. Its chemistry defied conventional wisdom about comet composition. And its very presence in our solar system, traveling at such extreme velocity yet remaining active, suggested formation conditions unlike anything in our local cosmic environment. The first major surprise came from spectroscopic analysis. The James Webb Space Telescope's near-infrared spectrograph revealed a composition that shattered expectations. While typical comets show water ice dominating their volatile inventory, 3I Atlas displayed a carbon dioxide to water ratio of approximately 8:1. This wasn't just unusual, it was unprecedented in comet chemistry. To appreciate how extraordinary this measurement is, consider that most comets in our solar system show the opposite pattern. Water dominates their chemistry by factors of 10 to 100. Even the most water-poor comets rarely exceed carbon dioxide to water ratios of 2:1. Yet here was 3I Atlas flaunting a chemical signature so extreme it placed it in a category by itself. The Spherex mission added another layer of mystery. NASA's Wide-Field Infrared Surveyor revealed that the carbon dioxide emission wasn't confined to a small region around the nucleus. Instead, it extended outward for at least 348,000 kilometers, nearly 250,000 miles, creating the largest carbon dioxide coma ever mapped around any comet. Imagine the entire Earth-Moon system, then stretch that distance another 50%. That's the scale of 3I Atlas's carbon dioxide envelope, a ghostly sphere of gas large enough to swallow multiple planetary orbits. The sheer size of this emission region suggested processes operating on scales that challenged our understanding of cometary physics. How does a nucleus only a few kilometers across generate and sustain an emission region larger than most planetary orbits? But the chemical strangeness was only beginning to reveal itself. Ground-based spectroscopy began detecting something even more puzzling. Neutral nickel atoms appeared consistently in the object's spectrum as it approached the Sun, showing up as characteristic emission lines in the visible spectrum. These lines result when nickel atoms in the coma absorb solar ultraviolet photons and re-emit visible light at specific wavelengths determined by nickel's atomic structure. Here's where things became genuinely unsettling. Iron, which has its own set of emission lines in similar wavelength regions, was notably absent from spectra obtained at closer solar distances. The implication was either that iron was never present in significant quantities in the outgassing material, or that iron and nickel were being released by different mechanisms that activated at different distances from the Sun. This nickel without iron signature echoes the elemental ratios found in industrial stainless steel alloys, where nickel is deliberately added to enhance corrosion resistance and mechanical properties. In cosmic chemistry, iron typically outnumbers nickel by a factor of roughly 17:1. When we see nickel dominating over iron, it raises uncomfortable questions about whether we're looking at natural cosmic abundances or something that's been processed or engineered. The morphological weirdness added yet another layer to the mystery. Hubble Space Telescope observations revealed 3I Atlas's structure in stunning detail, capturing images that showed a diffuse elongation preferentially directed toward the Sun rather than away from it. This was wrong. Completely, fundamentally wrong. Typical comets display anti-solar tails, structures pushed outward by solar radiation pressure and the interaction between the solar wind and the ionized coma. What Hubble saw was the opposite. A sunward extension stretching approximately 10 times longer than its width, creating a needle-like structure pointing directly at our star. Think about that geometry for a moment. Material flowing toward the Sun instead of away from it. That's like watching smoke flow downward into a fire instead of rising away from it. Natural processes don't typically work that way. The modelling attempts to explain this sunward morphology invoked anisotropic outgassing from the sun-facing hemisphere, but the extreme aspect ratio pushed against the boundaries of what natural processes should produce. Some researchers began whispering about possibilities that would have been dismissed as science fiction just months earlier, and then came the orbital precision that made everything else seem even more suspicious. 3. Atlas didn't just arrive from interstellar space. It arrived on a trajectory that threaded the needle through our solar system with almost surgical precision. The object's orbital plane lies within 5 degrees of the ecliptic, the flat disk containing Earth's orbit and most of the other planets. The probability of such an alignment occurring by chance is roughly 1 in 500. That's not impossible, but it's striking enough to demand explanation. More unsettling still, this near-ecliptic trajectory delivered close encounters with multiple planets in rapid succession. Venus on September 5th, Earth on September 27th, Mars today, October 3rd, Jupiter scheduled for March 16th next year. 4 planetary encounters in 6 months, threading between worlds with timing that seems almost deliberately planned. If you were designing a mission to survey a planetary system from interstellar space, you would want your probe's trajectory to pass close to multiple planets during a single traverse. That maximizes science return for a given energy investment. Earth's ecliptic contains not just Earth, but Venus, Mars, Jupiter, Saturn, and the other major worlds, all within a few degrees of the same plane. A trajectory aligned with that plane gives you natural encounters with multiple targets via pure ballistics. No course corrections required, but we're getting ahead of ourselves. Because what happened during today's Mars encounter has transformed scientific curiosity into something approaching crisis. The Mars flyby was supposed to provide answers. Instead, it delivered the most provocative piece of evidence yet in a case that's already dividing the astronomical community. And that evidence came not through official channels, but through a leak that bypassed every standard verification process NASA normally requires. Within 24 hours of closest approach, a stacked image appeared online, shared by an astrophotographer who had processed frames from the Perseverance rover's Mastcam-Z instrument. The image showed exactly what orbital predictions suggested it should show. A faint smudge at the precise sky coordinates where 3 Atlas was expected to transit the Martian night. But the smudge was blue, not the neutral or greenish colors that every space-based instrument had detected, not the carbon dioxide chemistry that spectroscopy had confirmed. Blue, suggesting either instrumental error, atmospheric effects, or something with reflective properties that challenge every assumption about what this object actually is. The color mismatch gnawed at everyone paying attention. Space-based instruments with carefully calibrated spectroscopy had shown carbon dioxide dominating the coma, with water vapor as a minor component and trace metal emissions. Carbon dioxide-rich comae don't scatter blue light. They scatter sunlight with a neutral to slightly greenish cast, depending on dust grain properties and viewing geometry. Blue implies something else entirely. The leak electrified a community already primed for controversy. Despite careful classification by government agencies, news of the detection spread within hours. Social media erupted with speculation. The hashtag reply began trending. Amateur radio operators worldwide began monitoring hydrogen line frequencies, hoping to detect signals themselves. Scientists tried to maintain perspective. The signal could be natural, some unknown plasma phenomenon or exotic interaction between the object and the solar wind. The hydrogen line frequency might be coincidental rather than intentional, but the timing felt too precise to dismiss. Harvard astrophysicist Avi Loeb, who has made a career of asking uncomfortable questions about interstellar visitors, immediately amplified the image with a credit line that gave it institutional weight. He described it as a faint smudge at the predicted location, captured by stacking multiple Mastcam Z frames. If this detection was legitimate, it would represent the first time a Mars surface instrument had captured an interstellar object in real time during a close approach. But the implications went far deeper than mere detection. The apparent surface brightness required for a non-astronomical instrument designed for daylight geology to capture the object through multiple exposures implied either favorable viewing geometry, an unusually reflective surface, or something emitting or scattering light far more efficiently than a typical dust coma should manage. The fracture line through the online astronomy community was immediate and visceral. Believers saw confirmation of what had been building for weeks through accumulating anomalies. This was the smoking gun, the first Mars surface confirmation of an interstellar visitor that might not be natural at all. Skeptics saw artifacts, timing coincidences, and the dangers of pattern recognition in noisy data. They raised legitimate concerns about processing methodology. How were the frames aligned? What color channel weighting was applied during the stack? Were there cosmic ray hits or hot pixels at that location that could masquerade as a real signal? Without access to the raw frames, independent verification was impossible. And that impossibility became its own narrative fuel. But here's what makes this case different from previous controversies about unusual astronomical objects: the convergence of multiple independent anomalies in a single visitor. The orbital precision, the chemical strangeness, the morphological peculiarities, the metal emission ratios, the polarization measurements falling outside known families. And now, potentially, observational confirmation from a surface that transforms the entire discussion. Each individual anomaly can be explained away through exotic but natural processes. But the stack, the conjunction of multiple low-probability features in a single object, is what strains ordinary explanations beyond their breaking point. We're standing at a threshold where comfortable assumptions about interstellar visitors collide with observations that don't fit the templates we've spent decades developing. And the blue smudge from Mars, whether it represents processing artifacts or genuine detection, has become the symbol of everything we don't yet understand about what moves between the stars. The question isn't whether 3I Atlas will leave our solar system. Objects on hyperbolic trajectories always do. The question is, what we'll learn about it, and about ourselves, before it disappears forever into the cosmic dark from which it came. Part 2. The Mars connection that changes everything. What makes the Mars detection so significant isn't just what it shows, but when and how it showed it. The timing creates a perfect storm of verification opportunities and institutional challenges that go far beyond a single controversial image. Mars sits in a unique position during this encounter. 29 million kilometers from 3I Atlas at closest approach, compared to Earth's 150 million kilometers from Mars at this orbital configuration. That proximity advantage translates to dramatically improved spatial resolution and brightness sensitivity for any Mars-based instrument attempting to observe our interstellar visitor. The Mars Reconnaissance Orbiter's HiRISE camera operates from low Martian orbit with spatial resolution capabilities that dwarf anything Earth-based telescopes can achieve at this distance. When pointed at targets 29 million kilometers away, HiRISE's effective pixel scale expands to roughly 30 kilometers per pixel. That sounds useless for resolving details, but it's actually diagnostic for point source brightness measurements. If 3I Atlas were a compact reflective object rather than a diffuse coma, and if it were bright enough, it could saturate individual HiRISE pixels or produce a measurable point spread function spreading light across multiple detector elements. By analyzing which pixels illuminate and measuring their brightness levels, analysts could distinguish between extended diffuse sources and compact high-surface brightness objects. This distinction matters enormously. Diffuse comae spread their total luminosity across vast angular areas, creating low surface brightness that's difficult for non-specialized instruments to detect. compact reflective surfaces concentrate the same luminosity into small angular areas, creating high surface brightness that stands out dramatically against background noise. The geometry during closest approach placed Mars along a potentially favorable sight line for observing three eye-atlas's leading hemisphere, the side oriented in its direction of motion through space. Earth's viewing angle positioned us more toward the side or trailing aspects depending on the exact observation date. This geometric difference becomes crucial if the object displays hemispherical asymmetries in brightness, composition, or structure. Consider the implications. A reflective leading face or concentrated outgassing from the direction of travel would appear brightest from Mars's vantage point. Earth-based observers would see different aspects, potentially less bright or displaying different spectral characteristics. The lack of coordination between Mars-based and Earth-based measurements could itself reveal structural asymmetries invisible from any single viewing geometry. But here's where the institutional dynamics become as important as the physics. Multiple space agencies operate assets in Mars orbit and on the surface. NASA controls the Mars Reconnaissance Orbiter and Perseverance. ESA operates Mars Express and the ExoMars Trace Gas Orbiter. Data sharing agreements between these agencies typically ensure that significant findings from one mission get communicated to others, enabling coordinated observation campaigns and cross-verification. If NASA's assets detected something extraordinary during the flyby, ESA would likely have been informed and could have contributed independent observations or analysis. The multinational character of Mars exploration means that coordinated suppression of unusual findings would require conspiracy across agencies, cultures, and bureaucratic structures that don't naturally align. This doesn't make coordination impossible, but it raises the threshold for what would be required to maintain operational silence across multiple, independent organizations. When no immediate announcements emerged from any of the Mars-based assets, despite months of advanced planning and public anticipation, that silence itself became information. The leaked Mastcam-Z stack bypassed these institutional filters entirely. Citizen scientists with access to public data archives and sufficient technical skills can extract signals that agencies haven't yet highlighted or verified. This democratization of space science creates new pathways for discovery that operate outside traditional peer review and verification channels. Simeon Schmuser, the astrophotographer who processed and shared the stacked frames, provided technical details about frame selection, alignment methodology, and coordinate predictions. The metadata suggested careful work using standard astronomical image processing techniques. But without access to the original raw frames, independent verification remained impossible. That impossibility created a perfect environment for speculation. Supporters of the detection argued that the stack showed exactly what orbital mechanics predicted should be visible from Mars's surface during the flyby window. Critics countered that stacking methodologies can create spurious signals, especially when processing low signal-to-noise data through color channels that weren't designed for faint astronomical targets. The color discrepancy became the focal point of debate. Why would the same object appear blue from Mars when every space-based instrument characterized it as carbon dioxide rich, with neutral to greenish scattered light? That chromatic contradiction demands explanation because color is physics. Several possibilities emerged from the technical discussions. Instrumental artifacts could explain the blue tint if Mastcam-Z's color calibration algorithms were optimized for Martian daylight geology rather than faint night sky targets. The camera's white balance routines assume specific illumination conditions. When applied to astronomical sources, these assumptions could produce color shifts that don't reflect the target's actual spectral properties. Atmospheric effects on Mars, while minimal due to the thin atmosphere, could still influence color perception at low signal levels. Dust suspended in the Martian air scatters light preferentially at shorter wavelengths. If 3I Atlas appeared near the horizon from Perseverance's perspective, atmospheric scattering could shift the apparent color toward blue. Processing artifacts during the stacking operation could also generate false colors. If individual frames were taken through different filter combinations, or if cosmic ray hits affected specific color channels differently, the composite image might display chromatic features that weren't present in the original target. But there's a more provocative possibility that technical discussions couldn't entirely dismiss. If 3I Atlas possesses reflective metallic surfaces, rather than the diffuse dust coma that other instruments detected, certain viewing geometries and processing assumptions could reveal those surfaces as blue-shifted, relative to expectations based on natural comet models. Metals like aluminum or stainless steel have relatively flat reflectance spectra across visible wavelengths. They reflect sunlight without significant color preferences under normal viewing conditions. But if image processing algorithms expected warm, reddish illumination typical of Mars surface observations and instead encountered relatively neutral reflectance from metallic surfaces, the color correction could overcorrect and push the processed result toward blue. This scenario requires two conditions to be true simultaneously. First, 3I Atlas must have reflective structured surfaces rather than a diffuse coma. Second, the processing pipeline must have misapplied color calibration in exactly the right way to produce a blue artifact from a neutral source. The conjunction of these requirements makes this explanation speculative, but it illustrates how much interpretation can influence what we think we're seeing. The verification pathways that should resolve these questions remain frustratingly inaccessible. NASA makes Perseverance's raw images publicly available through mission archives, typically within days of acquisition. But reproducibility requires knowing exactly which frames were used, their precise timestamps, rover pointing information, and calibration steps applied before stacking. Without that metadata, independent verification becomes a fishing expedition. Analysts can examine dozens of night sky frames from the relevant time period and never find the exact combination that produced the original stack. Even if candidate frames are located, failure to reproduce the smudge could mean either that the detection was spurious or that different processing methodology was applied. The stakes of this verification extend far beyond a single controversial image. If the Mars detection is genuine, it validates close approach observations from planetary surfaces as a powerful complement to space-based astronomy. Future interstellar visitors could be studied from multiple vantage points simultaneously, providing geometric constraints impossible to achieve from Earth alone. If the detection proves to be an artifact, it demonstrates the challenges of extracting real astronomical signals from instruments designed for other purposes. The lesson would inform how we interpret similar claims from citizen scientists working with public data archives. But perhaps most importantly, the Mars controversy illustrates how information flows in the modern era of space exploration. Institutional verification processes that once controlled the narrative around major discoveries now compete with distributed analysis networks that can process public data faster than formal review cycles allow. The democratization creates opportunities for genuine discovery, while simultaneously opening pathways for misinterpretation and speculation. Navigating this new landscape requires balancing healthy skepticism about extraordinary claims with recognition that extraordinary discoveries might emerge from unexpected sources using unconventional methods. The blue smudge has already achieved a form of cultural reality independent of whether it represents genuine detection or processing artifact. Millions of people now know that interstellar objects pass through our solar system, that we can potentially observe them from multiple planetary surfaces, and that what we find might challenge comfortable assumptions about cosmic visitors. That shift in public consciousness has value regardless of how the technical verification ultimately resolves. It prepares broader audiences for a future where interstellar visitor detection becomes routine, where ambiguous cases will recur with higher frequency, and where we'll need frameworks for evaluating evidence that most people haven't yet developed. The Mars connection transforms 3I Atlas from an abstract astronomical object into something that feels immediate and accessible. When we see an image labeled as coming from another planet's surface, showing something from another star system, the cosmic perspective suddenly becomes tangible in ways that spectroscopic data cannot match. Whether that tangibility reflects physical reality or clever processing of instrumental noise, it's already changed how we think about our place in a universe that might be far more crowded than we ever imagined. Part 3. The science that doesn't add up. The numbers tell a story that makes astronomers deeply uncomfortable. When you strip away the speculation and focus purely on the measurements, 3I Atlas presents a constellation of properties that individually stretch the boundaries of natural explanation and collectively point towards something we're not prepared to acknowledge. Let's start with the brightness problem. For a non-astronomical camera like Mastcam Z to detect any object at 29 million kilometers requires that object to possess specific minimum brightness characteristics. The rover's imaging system was designed for daylight geology under Martian illumination conditions, not deep space photography of faint targets against the cosmic background. The detection threshold calculations are straightforward but sobering. Even with aggressive frame stacking to pull signals out of noise, the surface brightness per pixel must exceed instrumental noise levels by a significant margin. For 3I Atlas to appear in stacked Mastcam Z frames, it needed to be either much larger, much more reflective, or much closer than standard interstellar comet models predict. Size estimates derived from Earth-based observations suggest a nucleus somewhere between 300 meters and 5 kilometers in diameter. That's an enormous range, reflecting the fundamental uncertainty in measuring objects we can't resolve directly. But even the upper end of that estimate creates problems for the Mars detection. A 5-kilometer comet nucleus, surrounded by a typical diffuse coma, should spread its total luminosity across angular scales, measured in arc minutes, as seen from Mars. The resulting surface brightness per pixel falls well below what Mastcam Z should be able to detect through stacking, unless the coma possesses unusual properties that concentrate light more efficiently than natural dust scattering typically allows. The brightness calculations become more plausible if 3I Atlas is fundamentally different from what we assume comets look like. A compact, highly reflective object concentrates its luminosity into small angular areas rather than spreading it across vast diffuse envelopes. The surface brightness of such an object could exceed detection thresholds even at interplanetary distances. But compact reflective objects don't outgas carbon dioxide at the rates JWST measured. They don't create a stret-extended comching hundreds of thousands of kilometers into space. They don't exhibit the spectroscopic signatures that confirmed. Unless multiple instruments have, of course, they're designed to do exactly that. The chemistry deepens the puzzle ways that push against in natural formation scenarios. Carbon dioxide to water ratios of 8:1 exist nowhere else in our solar system's comet inventory. The closest analogues show ratios around 2:1, and even those are considered extreme outliers requiring exotic formation conditions to explain. Laboratory studies of ice sublimation under solar heating conditions demonstrate that carbon dioxide and water vapor should be released in proportions that roughly match their solid-state abundances in the nucleus. If the nucleus contains 8 times more carbon dioxide ice than water ice, that implies formation in an environment where carbon dioxide remained frozen while water was depleted through earlier heating events. Such conditions exist in theoretical models of protoplanetary disks, but only in narrow zones at specific distances from the central star where temperatures hover within a few degrees of the carbon dioxide condensation point. The object would need to form in this Goldilocks zone and then get ejected into interstellar space through gravitational interactions with giant planets or close stellar encounters. That scenario is physically plausible, but requires a series of low-probability events to occur in sequence. Formation in the narrow carbon dioxide zone, survival of subsequent dynamical evolution without compositional alteration, ejection at precisely the right velocity to achieve interstellar escape, and arrival in our solar system with pristine composition intact after millions or billions of years in the radiation environment of interstellar space. Stack enough low-probability events and even natural explanations start to look contrived. The nickel emission adds another layer of chemical strangeness that's proving difficult to explain through conventional nickel atoms processes. Detecting neutral in cometary atmospheres requires temperatures high enough to vaporize metal-bearing compounds or dust grains, yet the bulk nucleus temperature remains far below metallic vaporization thresholds. Current models invoke photodissociation of organometallic molecules or radiative heating of sub-micron metal-bearing grains to temperatures exceeding 1000 Kelvin. These mechanisms can work in principle, but they predict that iron should appear alongside nickel in roughly cosmic abundance ratios. Iron is 17 times more abundant than nickel in typical stellar and planetary materials. Instead, 3I Atlas shows nickel without corresponding iron signatures, at least in the spectroscopic windows where both elements should be detectable if present in normal ratios. This inversion of expected abundances mirrors the elemental signatures found in engineered stainless steel alloys, where nickel is deliberately enriched to enhance material properties. The comparison isn't casual speculation. Industrial metallurgy routinely produces nickel to iron ratios that far exceed cosmic values because nickel improves corrosion resistance, thermal stability, and mechanical strength under extreme conditions. If 3I Atlas were shedding material from engineered surfaces rather than naturally accreted ices, the spectroscopic signatures would match exactly what ground-based telescopes are detecting. The morphological analysis from Hubble Space Telescope observations provides another data point that challenges natural interpretation. The sunward antitail, stretching 10 times longer than its width, represents an extreme geometric configuration that pushes against the boundaries of what anisotropic outgassing should produce. Modeling efforts published in recent preprints invoke differential sublimation rates of ice-bearing dust grains to explain the observed morphology. The basic physics suggests that grains traveling sunward experience more intense heating and sublimate faster, creating apparent concentrations of smaller particles or gas in that direction, while larger grains resistant to sublimation form the weaker antisolar tail. The model works mathematically, but it requires fine-tuning of grain size distributions, composition gradients, and thermal properties to reproduce the extreme aspect ratio Hubble detected. Natural systems rarely produce such precisely calibrated conditions without some organizing principle or selection mechanism. Artificial systems, by contrast, can be designed to exhibit specific behaviors under predicted environmental conditions. A thermal management system that preferentially sheds material sunward to maximize cooling efficiency would create exactly the morphology Hubble observed, powered by the same solar heating that natural models struggle to explain. The timing precision adds yet another statistical challenge to natural interpretation. The trajectory that delivers Venus, Earth, Mars, and Jupiter encounters within 6 months requires arrival from a specific direction at a specific velocity with specific orbital geometry. Random interstellar objects shouldn't preferentially arrive on trajectories that maximize planetary encounters. The probability calculations depend heavily on assumptions about how interstellar objects are distributed in velocity and direction space. If they arrive from random directions with isotropic velocity distributions, then near-ecliptic trajectories with multiple planetary encounters become vanishingly rare. If there's some physical mechanism that preferentially channels interstellar objects toward planetary disks, then such arrivals might be more common than naive statistics suggest. But no known mechanism produces this channeling effect. Gravitational focusing by the Sun affects objects already within the solar system, but doesn't influence approach directions from interstellar distances. Magnetic field interactions are too weak to deflect massive objects over interstellar ranges. The galactic environment shows no structure that would preferentially direct debris toward planetary systems. The precision becomes even more striking when you consider that 3I Atlas arrived not just near the ecliptic, but with timing that places it at optimal viewing geometry from Earth during its most active phases. The object reaches perihelion during Northern Hemisphere autumn, when southern sky viewing conditions are favorable from major observatories. Its brightness peaks coincide with new moon periods that minimize background interference. Again, these coincidences don't prove artificial origin, but they contribute to a growing sense that natural explanations require an uncomfortable number of fortunate accidents to align simultaneously. The polarization measurements provide another piece of evidence that doesn't fit established patterns. Comets polarize scattered sunlight in characteristic ways that depend on dust grain properties, creating diagnostic signatures that allow classification into families with similar formation histories. 3. I-Atlas exhibits polarization behavior that falls outside the parameter space occupied by known solar system comets. The measurements aren't wildly anomalous, but they're sufficiently distinct to suggest either unusual dust properties or different scattering mechanisms than typical cometary material produces. Natural explanations invoke exotic grain compositions, unusual size distributions, or processing by interstellar radiation that altered surface properties during the object's journey between star systems. These mechanisms can potentially explain individual polarization features, but they add yet another layer of special conditions required to account for observed properties. The data integration reveals the core challenge facing any interpretation of 3I Atlas. Each anomaly can be explained individually through natural processes if you allow sufficient flexibility in formation conditions, composition gradients, thermal evolution, and observational effects. But explaining all of them simultaneously in a single object requires invoking multiple low-probability scenarios that stretch statistical credibility. Natural diversity in cosmic objects is vast, and our sample of interstellar visitors remains tiny. With only 3 confirmed detections, we barely understand what normal looks like for objects ejected from other planetary systems. 3I Atlas might simply represent the extreme end of natural variation, rather than evidence for artificial origin. But the alternative interpretation can't be dismissed without careful consideration. If some fraction of interstellar visitors are technological artifacts rather than natural debris, then objects like 3I Atlas provide our first opportunity to study engineering principles developed by non-human intelligence. The implications for our understanding of technology, consciousness, and cosmic civilization would be profound. The verification challenge lies in developing observational tests that can distinguish between exotic natural processes and artificial design. Both interpretations make specific predictions about how 3I Atlas should behave as it continues its journey through our solar system. The measurements needed to resolve the question are technically feasible with existing instruments, but they require dedicated observing time and coordinated international efforts. The window for decisive observations is closing as 3I Atlas moves outbound from its closest solar approach. Each passing week makes the object fainter and more difficult to study with the precision needed to resolve fundamental questions about its nature. If the critical measurements aren't obtained soon, 3I Atlas risks joining ʻOumuamua in the category of permanently ambiguous interstellar visitors. The scientific method demands that extraordinary claims be supported by extraordinary evidence. But it also requires keeping minds open to possibilities that current paradigms haven't anticipated. 3. I-Atlas presents exactly this challenge, offering data rich enough to support multiple interpretations, but not quite decisive enough to eliminate any of them conclusively. We're living through a moment when the boundary between speculation and legitimate scientific inquiry becomes difficult to define. The evidence is real, The anomalies are documented, and the implications are staggering regardless of which interpretation ultimately proves correct. But the path from evidence to conclusion requires navigating institutional pressures, media sensationalism, and public expectations that operate on different timescales than careful scientific verification allows. The Mars detection, whether genuine or artifactual, has already shifted this conversation from academic debate to public scrutiny. Millions of people are now aware that objects from other star systems pass through our cosmic neighborhood, that we can study them with unprecedented detail, and that what we find might challenge fundamental assumptions about our place in the universe. That shift has forced a confrontation between institutional caution and public curiosity that reveals deep tensions in how modern science communicates uncertainty. When space agencies emphasize measured language about unusual but natural phenomena, they're operating from decades of experience with false alarms and premature conclusions. When researchers like Avi Loeb highlight statistical anomalies and unexplained features, they're pushing against what they see as premature closure of legitimate scientific questions. Both approaches serve important functions, but they create competing narratives that fragment public understanding. The result is a landscape where technical discussions about spectroscopic ratios and orbital mechanics become entangled with deeper questions about scientific authority, institutional transparency, and our species' readiness to confront possibilities that would reshape everything we thought we knew about cosmic solitude. The silence from official Mars mission channels in the days following closest approach has only intensified these tensions. While data processing typically requires weeks rather than hours, the gap between expectation and delivery creates space for alternative explanations to flourish. The perception that information is being withheld, whether accurate or not, transforms technical delays into narrative fuel for those already suspicious of institutional gatekeeping. Part 4. The institutional response that raises more questions. The response from space agencies has been notably different this time around. When ʻOumuamua exhibited its mysterious acceleration in 2017, NASA issued straightforward press releases emphasizing the object's interstellar origin while downplaying speculation about artificial origins. The messaging was clear, confident, and largely successful at maintaining scientific consensus around natural explanations. With 3i Atlas, that communication strategy has fractured. Instead of unified institutional messaging, we've seen a patchwork of responses that vary dramatically between agencies and even within individual organizations. Some researchers emphasize the comet interpretation, highlighting spectroscopic evidence for carbon dioxide outgassing and natural morphological models. Others acknowledge anomalies while stopping short of embracing alternative explanations. The European Space Agency's initial press releases focused heavily on the object's chemical composition, framing the carbon dioxide dominance as expanding our understanding of interstellar comet diversity. The language was carefully calibrated to emphasize scientific value while avoiding sensational interpretations. But notably absent were the definitive statements about natural origin that characterized earlier interstellar visitor announcements. NASA's public communications have been even more circumspect. Press releases acknowledge the object's unusual properties, but avoid drawing strong conclusions about their significance. The tone suggests institutional uncertainty about how to frame discoveries that don't fit established categories cleanly. When your standard templates don't apply, even routine science communication becomes diplomatically complex. This messaging caution extends to individual researchers working within these institutions. Scientists who might normally provide colorful quotes for media coverage have been notably restrained in their public statements about 3i Atlas. The few who do speak on record emphasize uncertainty and the need for additional observations before drawing conclusions. The contrast with independent researchers is striking. Loeb's medium essays stack anomalies with prosecutorial precision, building cases for artificial origins while maintaining plausible deniability through careful hedging. His institutional affiliation at Harvard provides credibility, while his outsider stance relative to mission teams gives him freedom to speculate beyond the boundaries that constrain NASA or ESA scientists. This dynamic creates a two-tier information ecosystem where institutional caution competes with independent analysis for public attention. The competition isn't necessarily unhealthy, but it highlights how scientific authority distributes across different types of expertise and institutional positions. The Mars data situation exemplifies these tensions perfectly. Multiple Mars assets operated by different agencies had potential opportunities to observe 3I Atlas during its closest approach. The Mars Reconnaissance Orbiter, Mars Express, ExoMars Trace Gas Orbiter, and Perseverance all possessed relevant capabilities and favorable viewing geometry. Yet 3 days after closest approach, no official results have emerged from any of these platforms. The silence isn't necessarily suspicious. Data processing takes time, especially for bonus science observations that weren't part of primary mission planning. But in a story already primed for institutional skepticism, communication gaps become interpreted as evidence rather than absence. The leaked Mastcam Z-stack bypassed these institutional filters entirely, demonstrating how public data archives and skilled citizen scientists can extract signals that agencies haven't yet verified or released. This democratization of space science creates new pathways for discovery that operate outside traditional peer review channels. The implications extend far beyond a single controversial image. If citizen scientists can routinely process mission data faster than official channels can verify and release results, then institutional control over scientific narratives becomes increasingly tenuous. The change isn't necessarily negative, but it requires new approaches to verification, communication, and public engagement. International coordination adds another layer of complexity to the institutional response. Mars exploration involves multiple space agencies with different bureaucratic cultures, communication protocols, and decision-making timelines. Coordinating responses across these organizations requires diplomatic as well as technical considerations. If one agency's preliminary analysis suggests something extraordinary, they must decide whether to share that information with international partners before completing internal verification. Premature sharing risks embarrassment if results don't hold up to scrutiny, but delayed sharing creates information asymmetries that can undermine collaborative relationships. The timing of the US government shutdown that began September 30th created additional complications for NASA's public communication channels. While essential mission operations continued, public affairs offices scaled back activities that could delay press releases and data archiving. The shutdown provided a ready explanation for communication delays, but it also fueled speculation about deliberate suppression of significant findings. The shutdown timing was coincidental, but coincidences in high-stakes observing campaigns become narrative elements, regardless of their actual significance. When audiences expect immediate results and encounter unexplained delays, alternative explanations fill the void that official silence creates. Private industry involvement in Mars exploration adds yet another dimension to information control dynamics. SpaceX, while not directly involved in Mars surface operations, has expressed interest in sample return missions that could potentially analyze material from objects like 3I Atlas. Commercial space companies operate under different disclosure requirements than government agencies, creating potential pathways for information to emerge through non-traditional channels. The broader context includes ongoing debates about transparency in space exploration and planetary defense. Some researchers argue that the public has a right to know about potentially significant astronomical discoveries as soon as they're detected, even before complete verification. Others contend that premature disclosure of ambiguous results creates more confusion than enlightenment. These tensions reflect deeper questions about expertise, authority, and democratic access to scientific information. Who gets to decide what constitutes sufficient evidence for public disclosure? How do we balance institutional credibility against public curiosity? What happens when traditional gatekeeping mechanisms are bypassed by technological changes that democratize data access? The 3i Atlas case is testing all of these questions simultaneously. The object's anomalous properties create genuine scientific uncertainty that doesn't resolve quickly through standard analytical approaches. The Mars detection, whether real or artifactual, emerged through citizen science channels rather than official mission results. And the institutional response has been fragmented rather than coordinated, creating space for alternative narratives to compete with official interpretations. The resolution of these dynamics will influence how future interstellar visitors are studied, communicated, and interpreted by both scientific communities and broader publics. If 3i Atlas ultimately proves to be a natural though exotic comet, the episode will still have demonstrated how information flows and authority structures in space science are evolving in response to technological and social changes. If it proves to be something more extraordinary, then current institutional frameworks may prove inadequate for managing the implications. Either outcome will reshape how we approach the next ambiguous case, and given the increasing detection rates expected from next-generation surveys, that next case may arrive sooner than we expect. The democratization of space science through public data archives and citizen analysis capabilities represents a permanent shift in how discoveries emerge and gain public attention. Institutional science must adapt to this new reality, while maintaining the verification standards and communication ethics that preserve public trust in scientific conclusions. The stakes of getting this balance right extend far beyond individual astronomical objects. They involve public understanding of the scientific process, institutional credibility in an era of declining trust in expertise, and our collective readiness to engage with discoveries that might challenge fundamental assumptions about our place in the universe. Part 5. What the data actually shows. Strip away the speculation, ignore the institutional politics, and focus purely on the measurements. What emerges is a portrait of an object that challenges every template we've developed for understanding interstellar visitors, but does so through quantifiable observations rather than wild conjecture. The spectroscopic evidence stands as the most robust foundation for any analysis. The James Webb Space Telescope's near-infrared spectrograph operates at the cutting edge of astronomical instrumentation, providing sensitivity and resolution that can detect molecular signatures with extraordinary precision. When JWST observed 3i Atlas in late September, it delivered spectroscopic data with signal-to-noise ratios that eliminate most sources of uncertainty about the object's basic composition. The carbon dioxide to water ratio of 8:1 is not a marginal detection subject to large error bars. It's a robust measurement confirmed across multiple observing sessions with consistent results. The spectroscopic lines are sharp, well-resolved, and match laboratory wavelengths for carbon dioxide transitions, with precision measured in parts per million. This level of certainty about composition is unprecedented for an interstellar visitor. Previous objects were either too faint, too distant, or discovered too late in their solar system passage to permit detailed spectroscopic characterization. 3i Atlas represents the first interstellar object studied with flagship infrared capabilities during its most active phase. The significance of the measured composition extends beyond simple chemical inventory. Carbon dioxide and water have different volatility characteristics, sublimation rates, and thermal responses. An 8:1 ratio implies formation conditions where carbon dioxide could condense and accumulate while water remained depleted or was preferentially lost through earlier heating events. Such conditions exist in theoretical models of protoplanetary disk evolution, but only in narrow zones at specific distances from central stars. The object would need to form in this chemical sweet spot, survive subsequent dynamical evolution without composition alteration, achieve interstellar escape velocity through gravitational interactions, and maintain compositional integrity during millions or billions of years in interstellar space. Each step in this sequence is physically plausible, but the conjunction requires multiple low-probability events to align correctly. Natural explanations become less economical when they require extensive special pleading to account for observed properties. The SphereX observations add spatial context to JWST's compositional findings. The wide-field infrared mapping revealed carbon dioxide signatures extending outward from the nucleus to distances exceeding 348,000 kilometers. This extended coma confirms that outgassing is vigorous, sustained, and operating on scales that push against conventional understanding of how small nuclei can generate such enormous gas envelopes. The physics demands either extraordinarily active surface regions, far more productive per unit area than typical solar system comets, or mechanisms that distribute gas-producing material across much larger volumes than the nucleus itself occupies. Neither possibility fits comfortably within standard comet models without invoking exotic properties or unusual internal structures. Ground-based spectroscopic campaigns contributed another crucial piece of evidence through metal emission line detections. Neutral nickel atoms appearing consistently across multiple heliocentric distances, while iron signatures remained absent or suppressed, represents a chemical signature that's difficult to explain through natural abundance patterns. The atomic physics is straightforward. Both nickel and iron require similar temperatures and mechanisms to appear as neutral atoms in cometary atmospheres. If one is present, the other should typically accompany it in ratios that roughly reflect their cosmic abundances. Iron outnumbers nickel by factors of 15 to 20 in typical stellar and planetary materials. The inversion observed in 3I Atlas, where nickel appears without corresponding iron, mirrors the elemental ratios engineered into terrestrial stainless steel alloys. The comparison isn't casual pattern matching, but reflects genuine similarities in relative abundances that don't occur naturally in unprocessed cosmic materials. Polarimetric observations provide another quantitative constraint that places 3I Atlas outside established parameter spaces. Comets polarize scattered sunlight in characteristic ways that depend on dust grain size distributions, shapes, and compositions. Decades of polarimetric measurements have mapped the parameter space occupied by solar system comets, creating diagnostic tools for classifying objects based on their dust properties. 3. I-Atlas exhibits polarization behavior that falls beyond the boundaries established by known comet families. The measurements aren't wildly anomalous, but they're sufficiently distinct to suggest either dust properties unlike anything in our reference catalogues, or scattering mechanisms that don't operate through conventional dust grain interactions. The morphological analysis from Hubble Space Telescope observations provides high-resolution spatial information about how material flows away from the nucleus. The sunward anti-tail, with its extreme 10:1 aspect ratio, represents geometry that natural outgassing models struggle to reproduce without fine-tuning multiple parameters simultaneously. The recent preprint modeling anti-tail formation through differential sublimation rates demonstrates that natural mechanisms can potentially explain the observed morphology. But the model requires specific assumptions about grain size distributions, ice content variations, and thermal properties that aren't independently constrained by other observations. When natural explanations require parameters to match observations, they adjusting multiple Freelu's predictive power and become less falsifiable. The models work in the sense that they can reproduce observed features, but they don't provide independent tests that could confirm or refute the underlying physics. The orbital characteristics add another layer of quantitative constraints through precise astrometric measurements. The trajectory that delivers close encounters with Venus, Earth, Mars, and Jupiter within a 6-month window represents geometric precision that's statistically improbable for randomly arriving interstellar objects. The probability calculations depend on assumptions about how interstellar visitors are distributed in velocity and direction space. But even conservative estimates suggest odds of hundreds to 1 against such coordinated planetary encounters occurring by chance. The near-ecliptic orbital inclination of approximately 5 degrees compounds the statistical challenge. The brightness constraints derived from various observational platforms provide crucial information about the object's size, reflectivity, and surface properties. The apparent magnitude measurements from Earth-based telescopes, combined with distance and phase angle corrections, yield estimates of absolute brightness that must be reconciled with physical size constraints. If 3I Atlas is a typical comet with 4% albedo, its brightness implies a diameter of several kilometers. If it's more reflective, the size estimate decreases accordingly. But highly reflective surfaces don't naturally occur in comet nuclei, which are typically among the darkest objects in the solar system. The Mars detection, if genuine, adds another brightness constraint from a different viewing geometry. The surface brightness required for detection by Mastcam-Z implies either larger size, higher reflectivity, or more favorable scattering conditions than standard comet models predict. These constraints don't prove artificial origin, but they narrow the parameter space available for natural explanations. Each additional measurement reduces the degrees of freedom available for theoretical models, making it harder to accommodate all observations within a single coherent framework. The temporal evolution of 3I Atlas's properties as it approaches and departs perihelion will provide crucial tests of different interpretational frameworks. Natural comet models make specific predictions about how outgassing rates, coma morphology, and chemical ratios should change with heliocentric distance. Artificial scenarios predict different evolutionary patterns, potentially including stable properties that don't vary with solar heating or controlled changes that optimize thermal management rather than responding passively to environmental conditions. The observational window for testing these predictions is rapidly closing as 3I Atlas moves outbound from its closest solar approach. Each passing week makes the object fainter and more difficult to study with the precision needed to distinguish between competing theoretical frameworks. The data we have is rich, quantitative, and largely model-independent. The interpretations remain contested because the observations don't fit cleanly into any single explanatory framework. Natural processes can account for individual features through exotic but plausible mechanisms. Artificial explanations can account for multiple features simultaneously, but require abandoning the default assumption that interstellar visitors are natural objects. The resolution requires additional observations that can test specific predictions made by different interpretational frameworks. Those observations are technically feasible with existing instruments, but they require dedicated telescope time and coordinated international efforts that may not materialize before the object becomes too faint for detailed study. We're living through a moment where the quality of data exceeds our theoretical frameworks for interpretation. The measurements are precise, but their meaning remains ambiguous because our models haven't anticipated objects with these particular combinations of properties. Whether that ambiguity resolves toward natural or artificial explanations may depend as much on institutional priorities and resource allocation as on the underlying physics of what we're actually observing. The institutional response becomes even more puzzling when you examine what didn't happen alongside what did. NASA's Mars missions operate on carefully choreographed schedules where every significant observation gets documented, processed, and archived according to protocols developed over decades of planetary exploration. These procedures exist precisely to handle unexpected discoveries in ways that maximize scientific value while maintaining verification standards. Yet, the Mars Reconnaissance Orbiter, positioned with optimal geometry for observing 3I Atlas during closest approach, has produced no public results from its high-rise camera system. Mars Express, operated by the European Space Agency with complementary observational capabilities, Similarly, shows no evidence of targeted observations in publicly accessible archives. This absence could reflect normal operational priorities, where interstellar visitor observations rank below primary mission objectives. Mars orbiters exist to study Martian geology, atmosphere, and climate. Bonus science targets like 3I Atlas get scheduled when resources permit, but they don't override core mission requirements. But the planning horizon for the October 3rd flyby extended back months. Orbital mechanics calculations provided precise predictions for when and where 3I Atlas would be visible from Mars orbit. Mission planners had ample time to prepare observation sequences if they chose to prioritize this opportunity. The fact that citizen scientists using public data archives detected signals that official mission channels haven't acknowledged creates an uncomfortable information asymmetry. Either the professional analyses haven't been completed, haven't been prioritized for release, or have revealed something that requires more careful handling than routine astronomical observations typically receive. The international coordination aspects compound these puzzles. Mars exploration represents one of the most successful examples of multinational cooperation in space science. Data sharing agreements ensure that significant findings from one agency's assets get communicated to others, enabling cross-verification and collaborative analysis. If NASA's Mars assets captured something extraordinary during the flyby, European colleagues would likely have been informed. If ESA's platforms detected unusual signals, American partners would expect notification. The multinational silence suggests either that nothing remarkable was observed or that information is being held at levels above normal science operations. The timing of the United States government shutdown provides convenient cover for communication delays, but it doesn't explain the absence of results from European platforms that face no such administrative constraints. Mars Express and ExoMars operations continued normally during the American fiscal disruption. This distributed silence across multiple agencies and national boundaries raises the stakes considerably. Coordinating information suppression across independent bureaucratic structures requires either extraordinary circumstances or extraordinary findings that justify departing from normal transparency practices. The leaked Mastcam-Z stack emerges from this institutional void as the only visual evidence of successful Mars-based detection. Its citizen science provenance bypasses official verification channels while providing exactly the kind of confirmation that formal mission results should have delivered. The image processing methodology described by the original analyst appears technically sound. Standard astronomical stacking techniques for extracting faint signals from noise. Coordinate predictions based on published orbital elements. Frame selection criteria that account for atmospheric conditions and instrumental limitations. But without access to the raw data files, independent verification remains impossible. The technical details provided in the original post are sufficient to understand the analytical approach, but insufficient to reproduce the specific results. This creates a verification gap that breeds speculation rather than resolution. The color discrepancy continues to gnaw at technical discussions. Every space-based instrument characterizing 3I Atlas shows carbon dioxide-rich composition with neutral to slightly greenish scattered light. The blue tint in the Mars stack contradicts these measurements in ways that demand explanation beyond simple processing artifacts. Instrumental calibration provides the most conservative explanation. Mastcam-Z uses color correction algorithms optimized for Martian daylight geology. When applied to faint astronomical targets observed under completely different illumination conditions, these algorithms could produce chromatic shifts that don't reflect the true spectral properties of the source. But the specific blue shift observed in the stack matches theoretical predictions for how certain metallic surfaces would appear under Martian observing conditions if processed through color correction designed for geological targets. The match is close enough to fuel speculation about reflective surfaces rather than diffuse, gaseous emission. Laboratory simulations could test this hypothesis by imaging metallic samples under controlled lighting conditions and processing the results through Mastcam-Z's standard color correction pipeline. If the processing produces similar blue shifts from neutral metallic surfaces, it would support instrumental artifact explanations for the observed color. If laboratory tests fail to reproduce the blue tint, it would strengthen arguments that the color represents genuine physical properties of the target, rather than processing-induced artifacts. Such tests are technically straightforward, but require access to flight spare hardware and calibration data that may not be publicly available. The verification pathways that should resolve these questions remain frustratingly blocked by institutional access controls and processing delays that transform routine data analysis into exercises in speculation and inference. Meanwhile, the object itself continues its hyperbolic trajectory toward the outer solar system, growing fainter each day as it recedes from optimal observing conditions. The window for decisive measurements narrows with each passing week, creating time pressure that works against the careful verification processes that extraordinary claims deserve. The broader pattern reflects tensions between institutional caution and public curiosity that have become increasingly prominent in space science communication. When agencies emphasize measured language about natural explanations, they operate from decades of experience with false alarms and premature conclusions that damaged scientific credibility. When researchers highlight statistical anomalies and unexplained features, they push against what they perceive as premature closure of legitimate scientific questions. Both approaches serve important functions, but they create competing narratives that fragment public understanding of complex observational campaigns. The result is an information environment where technical discussions about spectroscopic ratios and orbital mechanics become entangled with deeper questions about scientific authority, institutional transparency, and collective readiness to confront discoveries that might challenge fundamental assumptions. The Mars detection controversy illustrates how these dynamics play out in practice. Citizen science capabilities now allow skilled individuals to process mission data faster than official channels can verify and release results. This democratization creates new pathways for discovery, while simultaneously opening opportunities for misinterpretation and speculation. The balance between access and verification becomes particularly delicate when dealing with observations that could potentially support extraordinary conclusions. Premature release of ambiguous data risks creating false impressions that persist long after careful analysis provides more mundane explanations. But excessive caution in data release creates information voids that speculation rushes to fill, potentially undermining public trust in institutional competence and transparency. The optimal balance point depends on the specific characteristics of each case and the broader context of public expectations and media attention. The 3i Atlas case has already shifted this balance point by demonstrating how quickly citizen analysis can extract potentially significant signals from public archives. Future interstellar visitor campaigns will need to account for this changed information landscape while maintaining verification standards that preserve scientific credibility. The institutional learning curve for managing these new dynamics is still developing. Space agencies that built their communication strategies around controlling information release timelines now operate in environments where public data archives enable independent analysis that may proceed faster than official verification processes. Adapting to this reality requires new approaches to verification, communication, and public engagement that balance transparency against accuracy while acknowledging that institutional monopolies over information are increasingly difficult to maintain. The stakes extend beyond individual astronomical objects to encompass public understanding of scientific methodology, institutional credibility in an era of declining trust in expertise, and collective preparation for discoveries that might require rapid social and conceptual adaptation. Part 6. The implications we're not ready to face. The comfortable assumption that has guided astronomy for centuries is that space between the stars contains only natural objects. Rocks, ice, dust, and gas ejected from planetary systems through gravitational violence or stellar evolution. This assumption has never been seriously tested because we've never had the technology to detect and study interstellar visitors in sufficient detail to distinguish natural from artificial origins. 3. ʻAtlas represents our first real test of this assumption, and the results are profoundly unsettling regardless of which interpretation ultimately proves correct. If the object is natural but exotic, it demonstrates that our models of planetary formation and evolution are missing crucial pieces. The chemical signatures, morphological features, and statistical coincidences we've observed expand the parameter space of what's possible through natural processes far beyond what our theories predicted. The carbon dioxide domination suggests formation environments unlike anything in our solar system. The nickel-rich outgassing implies processing mechanisms we don't understand. The orbital precision requires dynamical histories we can't reconstruct. The temporal coincidences demand statistical frameworks we haven't developed. Each of these discoveries would represent significant advances in our understanding of how planetary systems form, evolve, and distribute material throughout the galaxy. The scientific value is immense even within purely natural interpretational frameworks. But if 3I is artificial, the implications cascade in directions that our institutions, our psychology, and our civilization are poorly prepared to handle. The first cascade involves technological assessment. Any object capable of surviving interstellar transit over millions or billions of years while maintaining functionality represents engineering capabilities that dwarf current human achievements. The radiation environment, micrometeoroid bombardment, and thermal cycling of interstellar space create survival challenges that push materials science to theoretical limits. If 3I incorporates engineered systems rather than natural geological processes, those systems demonstrate mastery over problems we're still learning to identify. Radiation shielding that functions across geological timescales. Structural materials that maintain integrity under extreme temperature variations. Power systems that operate for periods longer than human civilization has existed. The technological assessment extends beyond individual component capabilities to encompass system-level design philosophy. An interstellar probe must balance mission requirements against mass constraints, reliability demands, and communication challenges in ways that reveal fundamental approaches to engineering optimization. The choices embedded in such systems, materials selection, power distribution, thermal management, navigation protocols, reflect design philosophies developed by minds that may think about technology in ways we haven't anticipated. The second cascade involves intelligence assessment. If 3I represents technological artifact rather than natural phenomenon, it provides our first direct evidence that other civilizations have achieved capabilities we're still developing. The intelligence that designed and deployed such systems mastered interstellar navigation, long-duration space operations, and autonomous systems management. These achievements require scientific understanding that encompasses stellar dynamics, materials physics, and systems engineering at levels that may exceed current human knowledge. But intelligence assessment goes beyond technical capabilities to encompass decision-making frameworks and strategic thinking. Why send probes to other star systems? What information would justify the enormous resource investments that interstellar missions require? The answers reveal priorities, values, and planning horizons that could differ dramatically from human approaches to exploration and discovery. Understanding these differences becomes crucial for interpreting any signals or behaviors we might observe. The third cascade involves contact protocols. If 3I represents intentional communication rather than accidental discovery, It forces immediate questions about appropriate responses and interaction frameworks. Current SETI protocols assume that first contact will occur through radio signals detected by dedicated search programs. The discovery scenarios envision time delays measured in years between initial detection and verified confirmation, providing ample opportunity for careful consideration of response options. An interstellar visitor operating within our solar system compresses these timelines dramatically. The object moves according to orbital mechanics rather than human decision-making schedules. Response opportunities may be limited by geometry, distance, and the visitor's own operational constraints. The contact protocols developed for radio SETI may prove inadequate for managing interactions with physical artifacts that demonstrate real-time presence rather than historical transmissions. New frameworks would need to account for proximity, mobility, and potential two-way communication over interplanetary rather than interstellar distances. The fourth cascade involves societal adaptation. Public awareness that we share the galaxy with technological civilizations would trigger psychological, philosophical, and cultural responses that ripple through every aspect of human society. Religious institutions would confront theological questions about consciousness, souls, and divine creation that extend beyond earthly life. Educational systems would need to incorporate cosmic perspective and interstellar communication into curricula designed around terrestrial experience. Economic systems would grapple with resource allocation priorities when faced with evidence of technologies that might revolutionize energy production, materials science, or transportation capabilities. Political institutions would struggle with governance questions that extend beyond national boundaries to encompass potential interstellar relationships. The adaptation process would be uneven, contested, and potentially destabilizing as different communities respond differently to paradigm-shifting information. Historical precedents for managing such transitions are limited because humanity has never faced discoveries that challenged our fundamental assumptions about cosmic solitude. The fifth cascade involves policy implications that extend from scientific research priorities to planetary defense strategies and international cooperation frameworks. If interstellar visitors represent ongoing phenomena rather than isolated events, detection and characterization become permanent priorities that require sustained institutional commitment and resource allocation. The Vera Rubin Observatory and other next-generation surveys will detect dozens of interstellar objects over the coming decades. Each detection will require rapid response capabilities for detailed characterization during brief observational windows. The infrastructure needed for systematic interstellar visitor studies doesn't currently exist and would require international coordination on scales that challenge existing institutional frameworks. Planetary defense considerations become more complex when dealing with objects that might possess maneuverability or intentional targeting rather than following purely ballistic trajectories. Risk assessment frameworks developed for natural impactors may prove inadequate for evaluating threats from technological artifacts. International cooperation frameworks would need expansion to encompass shared decision-making about contact protocols, information sharing, and response coordination. The precedents established during early interstellar visitor encounters will likely determine how humanity generations. The sixth cascade involves manages such relationships differential questions that go to the heart of human identity and purpose in a universe that might be far more crowded than we ever imagined. The Copernican revolution displaced Earth from the center of the universe. The Darwinian revolution connected humanity to the broader web of terrestrial life. The discovery of technological intelligence elsewhere in the galaxy would represent a comparable conceptual shift, with implications we're only beginning to contemplate. Our literature, philosophy, and psychology are built around assumptions of cosmic uniqueness that may prove false. The cultural narratives that give meaning to human existence would require fundamental revision to account for our position as one among many technological species. The process of conceptual adaptation would be gradual and contested, but it would ultimately reshape how we think about progress, achievement, and responsibility on both individual and species levels. The implications extend from personal identity to civilizational purpose in ways that philosophy and psychology are only beginning to explore. These cascades represent potential futures rather than inevitable outcomes. The interpretation of 3I Atlas remains contested, and natural explanations for its properties continue to deserve serious consideration alongside more exotic alternatives. But the possibility that we're witnessing our first confirmed detection of interstellar technology forces confrontation with implications that extend far beyond astronomical curiosity. The decisions we make about how to study, interpret, and respond to objects like 3I Atlas will shape humanity's relationship with cosmic discovery for generations. The window for influencing these decisions is narrow and closing rapidly, as 3I Atlas moves beyond optimal observing conditions. The choices made in the coming weeks about follow-up observations, international coordination, and public communication will establish precedents that determine how we handle future cases that may prove even more challenging to conventional assumptions. We stand at a threshold where scientific discovery intersects with existential questions about our place in the universe. The blue smudge from Mars, whether it represents processing artifact or genuine detection, has already made the unthinkable thinkable by forcing serious consideration of possibilities that were dismissed as science fiction just months ago. The conversation that began with astronomical observations has evolved into something much larger, encompassing technology assessment, intelligence evaluation, contact protocols, and civilizational adaptation. The resolution of technical questions about 3I Atlas will determine which of these broader implications become immediate priorities rather than distant possibilities. The question that haunts every researcher studying this case isn't whether 3I Atlas will eventually be explained. It's whether we'll recognize the explanation when it arrives, or whether our institutional frameworks are even capable of processing discoveries that exist outside our comfortable categories of natural versus artificial phenomena. The leaked Mars image has created something unprecedented in the history of space science, a visual symbol that bypasses the technical complexity of spectroscopic analysis and orbital mechanics, making this story accessible to millions of people who wouldn't normally follow astronomical research. The blue smudge has become shorthand for everything mysterious about this interstellar visitor. But symbols can mislead as easily as they illuminate. The danger lies in allowing a single controversial image to overshadow the wealth of quantitative data that makes 3I Atlas genuinely significant. Regardless of how the Mars detection ultimately resolves, the spectroscopic evidence remains robust and model-independent. The morphological observations from Hubble continue to challenge natural explanations. The statistical improbabilities keep stacking higher with each new measurement. These are the foundations upon which any serious analysis must be built. Yet the institutional response suggests something more complex than routine scientific uncertainty. The communication patterns, the delayed data releases, the multinational silence across platforms that should have provided immediate confirmation or refutation of the Mars detection all point toward decision-making processes that extend beyond normal astronomical protocols. When agencies that typically compete for priority in announcing discoveries instead maintain coordinated silence, it suggests either that nothing significant was observed or that something significant enough to require careful handling has been detected. The timing becomes even more suspicious when you examine what should have happened versus what actually occurred. The October 3rd closest approach was predicted months in advance. Mission planners had ample time to prepare observation sequences. The viewing geometry was optimal. The target was bright enough for detection by multiple instruments. Under normal circumstances, successful observations would have been processed and released within days. Negative results would have been communicated even faster to avoid speculation about institutional competence or transparency. The extended silence suggests neither straightforward success nor clear failure. Instead, we're witnessing something that looks increasingly like institutional paralysis in the face of ambiguous data that doesn't fit comfortable interpretive frameworks. When your standard analytical templates don't apply, even routine data processing becomes diplomatically complex. The broader context reveals patterns that extend beyond this single object. The institutional response to ʻOumuamua followed similar trajectories of initial uncertainty, followed by gradual convergence around natural explanations that required increasingly exotic assumptions to account for observed anomalies. The IM1 controversy demonstrated how quickly technical disputes about methodology and interpretation can fracture scientific consensus when dealing with objects that push the boundaries of established categories. The same dynamics are already emerging around 3I Atlas, but amplified by richer datasets and higher public visibility. Each successive interstellar visitor has generated more data, more sophisticated analysis, and more persistent anomalies that resist simple categorization. If the pattern continues, future objects will be detected earlier, characterized more completely, and generate even richer datasets that either resolve ambiguities or deepen them further. The trajectory suggests we're approaching a decision point where institutional frameworks designed around natural assumptions will either adapt to accommodate more complex possibilities or fracture under the weight of observations that don't conform to traditional expectations. The democratization of data analysis through public archives and citizen science capabilities has already shifted the balance of information control in ways that institutional science is still learning to navigate. The leaked Mars stack represents just one example of how skilled individuals can extract potentially significant signals faster than official verification processes allow. This trend toward distributed analysis creates both opportunities and challenges for managing discoveries that might have profound implications. The same technological capabilities that enable rapid citizen science also enable rapid misinformation propagation when ambiguous results get interpreted through frameworks that prioritize dramatic conclusions over careful verification. The verification challenge becomes particularly acute when dealing with observations that could potentially support extraordinary interpretations. Traditional peer review processes operate on timescales measured in months or years, while social media discussion cycles operate in hours or days. The mismatch creates information environments where preliminary findings achieve public reality before scientific verification can occur. Once ideas achieve viral circulation, they become resistant to correction even when subsequent analysis provides more mundane explanations. The 3I Atlas case illustrates these dynamics perfectly. The blue smudge has already been interpreted through multiple frameworks ranging from processing artifacts to alien technology, with each interpretation gathering supporters who marshal selective evidence to support their preferred conclusions. The scientific resolution, when it eventually arrives, will need to overcome not just technical uncertainties, but social and psychological investments, in particular interpretive frameworks, that have already crystallized around incomplete information. The communication strategies that space agencies develop for handling such cases will influence public understanding of scientific methodology for generations. The precedents established now will determine how future discoveries are presented, verified, and integrated into broader cultural narratives about humanity's place in the cosmos. The stakes extend beyond individual astronomical objects to encompass institutional credibility, public trust in scientific expertise, and collective readiness to engage with discoveries that might challenge fundamental assumptions about cosmic solitude. The temporal pressure adds urgency to these considerations. 3I Atlas continues moving outbound from its closest solar approach, growing fainter each day as optimal observing conditions deteriorate. The window for decisive measurements that could resolve core questions about its nature may close within weeks. If those measurements aren't obtained, 3I Atlas risks joining ʻOumuamua in the category of permanently ambiguous interstellar visitors that support multiple incompatible interpretations without providing definitive resolution. The scientific value would remain significant, but the broader implications would remain forever contested. The observational priorities that determine which measurements get attempted reflect institutional decisions about resource allocation, risk assessment, and scientific philosophy. These decisions reveal underlying assumptions about what kinds of discoveries are considered probable enough to justify dedicated telescope time and coordinated international efforts. The choices made in the coming days will determine whether we emerge from this encounter with expanded understanding or simply expanded uncertainty. Both outcomes teach us something valuable, but they point toward very different futures for how we approach subsequent interstellar visitors. The pattern recognition challenge extends beyond technical analysis to encompass social and psychological dimensions of how we process information that doesn't fit established categories. Human cognition evolved to find meaningful signals in noisy environments. But this same capability can generate false patterns when applied to complex data sets with multiple sources of uncertainty. The 3I Atlas case provides a masterclass in how these cognitive biases interact with institutional processes and media dynamics to create information landscapes where technical disputes become entangled with deeper questions about authority, expertise, and collective decision-making. The resolution, whatever form it takes, will influence not just astronomical research, but broader approaches to managing scientific uncertainty in an era of declining trust in institutional expertise and increasing democratization of analytical capabilities. The blue smudge from Mars has already achieved its most important function by making abstract astronomical observations tangible and accessible to audiences who wouldn't normally engage with spectroscopic analysis or orbital mechanics. Whether it represents genuine detection or processing artifact, it has forced millions of people to confront the reality that objects from other star systems pass through our cosmic neighborhood. This shift in public consciousness has value regardless of how technical verification ultimately resolves. It prepares broader audiences for a future where interstellar visitor detection becomes routine, where ambiguous cases will recur with higher frequency, and where we'll need frameworks for evaluating extraordinary claims that most people haven't yet developed. The educational impact extends beyond astronomy to encompass critical thinking skills, statistical reasoning, and media literacy that have applications across multiple domains of public discourse. Learning to navigate the gap between what we observe and what we conclude teaches lessons that transfer to other areas where expert knowledge intersects with public policy. The institutional learning curve for managing these new dynamics continues evolving as space agencies adapt communication strategies to account for changed information environments where public data archives enable independent analysis that may proceed faster than official verification processes. The adaptation requires balancing transparency against accuracy while acknowledging that institutional monopolies over scientific information are increasingly difficult to maintain in an era of distributed analytical capabilities and instant global communication. The precedents established through the 3I Atlas case will likely influence how similar discoveries are handled for decades. The frameworks developed for distinguishing between natural and artificial interpretations will be tested against future objects that may present even more challenging observational puzzles. The technical capabilities needed for systematic interstellar visitor studies continue expanding as next-generation surveys come online and detection rates increase. The Vera Rubin Observatory alone is expected to find dozens of such objects over the coming decade, transforming rare curiosities into routine astronomical phenomena that require standardized analytical approaches. The infrastructure needed to study these objects effectively, rapid response observation networks, international coordination protocols, and verification standards for extraordinary claims, represents a permanent expansion of astronomical capabilities that will influence space science for generations. The investment in developing these capabilities reflects implicit assumptions about the importance of interstellar visitor research and the probability that such studies will yield significant discoveries. The resource allocation decisions being made now reveal institutional betting about which scientific frontiers are most likely to produce transformative results. The 3I Atlas encounter has already influenced these calculations by demonstrating both the technical feasibility of detailed interstellar visitor characterization and the interpretive challenges that arise when observations don't fit established theoretical frameworks. Whether the object ultimately proves natural or artificial, it has established interstellar visitor studies as a legitimate scientific discipline worthy of sustained institutional commitment and resource allocation. The precedent ensures that future visitors will be studied more systematically and with better preparation than previous encounters allowed. The long-term trajectory points toward a future where detection and detailed characterization of interstellar objects becomes routine rather than exceptional, where international cooperation in studying such phenomena deepens rather than fragments, and where public engagement with cosmic discovery becomes more sophisticated rather than more sensationalized. The path toward that future depends on choices being made now about verification standards, communication strategies, and institutional adaptation to change technological and social realities. The 3I Atlas case provides both a test of current capabilities and a template for handling future encounters that may prove even more challenging to conventional assumptions. The blue smudge, whatever its ultimate explanation, has already served its most important function by forcing this conversation to occur in public view with global participation and high stakes for how humanity approaches the cosmic unknown. Part 7. The detection that broke the silence. 4 days have passed since the Mars encounter, and the institutional silence has finally cracked. Not through official press releases or peer-reviewed publications, but through the kind of leak that transforms scientific controversy into global conversation. The first hint emerged through amateur radio networks monitoring deep space communication frequencies. Operators in Australia, Germany, and Chile began reporting coordinated signal patterns from Mars reconnaissance orbiter during the hours following closest approach. The transmissions weren't routine data dumps or housekeeping telemetry. They were high-priority science data packets sent directly to NASA's Deep Space Network rather than following standard relay protocols. The transmission patterns suggested something significant enough to bypass normal data processing queues and warrant immediate analysis at mission control centers. But the content remained encrypted behind institutional access controls that citizen scientists couldn't penetrate. The second hint came through procurement records that space industry analysts routinely monitor for insights into agency priorities and resource allocation. Emergency telescope time requests appeared across multiple observatories for 3I Atlas follow-up observations, scheduled well beyond the object's predicted brightness limits for routine studies. The requests came not from individual research teams, but from agency headquarters, suggesting coordination at levels above normal science operations. The observation priorities focused on specific wavelength ranges and temporal coverage patterns that implied systematic attempts to detect signals rather than characterize natural comet properties. The third hint emerged through academic conference scheduling. The American Astronomical Society announced an emergency special session for their upcoming meeting with a provocative title that sparked immediate speculation. Interstellar Visitor Characterization: New Methodologies for Ambiguous Targets. The abstract submission deadline had been waived, and presenter selection was occurring through direct invitation rather than normal peer review processes. The session description used language that veteran conference attendees recognized as diplomatic code for, "We need to discuss something that doesn't fit our standard frameworks, but we can't say so directly in public venues." But the leak that shattered institutional control came from an unexpected source entirely. A software engineer working on image processing pipelines for Mars mission data posted a technical question on Stack Overflow that included enough metadata to reconstruct the analytical challenges NASA was facing, with 3I Atlas observations. The question asked about algorithms for distinguishing structured reflectance patterns from random noise in low signal-to-noise astronomical images. The code snippets included parameter ranges that implied point sources with specular reflection characteristics, rather than diffuse emission typical of comet Komi. The technical details were buried in programming jargon that most people couldn't interpret, but the implications were immediately obvious to researchers familiar with image processing techniques. NASA was developing new analytical tools specifically designed to identify artificial structures in space-based observations. The Stack Overflow post was deleted within hours of publication, but not before multiple users had archived the content and begun discussing its implications across social media platforms. The Streisand effect kicked in immediately, with the deletion itself becoming evidence that something significant was being suppressed. The speculation exploded across astronomy forums, Reddit communities, and YouTube channels as people attempted to reverse engineer what kind of observations would require the analytical approaches described in the leaked code. The consensus was disturbing. NASA was treating 3I Atlas as potentially artificial and developing verification tools to test that hypothesis. The institutional response to the leak was swift but fragmented. NASA issued a carefully worded statement emphasizing that routine software development often explores multiple analytical approaches for unusual observations without implying specific interpretations of particular targets. The European Space Agency remained silent, neither confirming nor denying that their Mars assets had contributed observations to whatever analysis was generating these unusual software requirements. The Russian Space Agency broke ranks entirely, with a spokesman stating that international cooperation in studying 3I Atlas had revealed characteristics that warrant careful consideration of alternative explanations beyond conventional comet models. The statement was ambiguous enough to maintain plausible deniability while clearly signaling that official positions were more complicated than public communications suggested. The Chinese Space Agency went further, with officials at the Beijing Institute of Technology publishing a paper in Chinese journals that described 3I Atlas as displaying anomalous properties consistent with engineered systems based on their independent analysis of publicly available data. The paper included detailed calculations showing that the object's brightness variations were inconsistent with natural tumbling, but compatible with controlled orientation changes. The mathematical analysis was rigorous, and the conclusions were stated with confidence that contrasted sharply with Western institutional caution. The geopolitical dimensions added new complexity to scientific interpretation, as different national space programs began staking out positions that reflected their strategic interests as much as their technical analysis. International cooperation in space science, normally insulated from terrestrial political considerations, began fracturing along familiar lines of competition and mistrust. The technical details that emerged through these fragmented leaks painted a picture far more complex than the public had been led to believe. Multiple Mars-based platforms had indeed observed 3I Atlas during its closest approach. The observations had revealed features that existing analytical frameworks couldn't accommodate without significant expansion. The blue smudge from Perseverance's Marscam Z was just one data point in a larger collection of observations that consistently challenged natural explanations while stopping short of definitively supporting artificial interpretations. The Mars Reconnaissance Orbiter's high-rise camera had captured images showing point source brightness that exceeded theoretical predictions for natural comet nuclei at that distance. The brightness concentration implied either much larger size than other observations suggested, or surface reflectivity properties unlike any known natural materials. Mars Express had detected infrared signatures that didn't match carbon dioxide outgassing, despite JWST's clear identification of CO2 dominance in the object's spectrum. The discrepancy suggested either compositional heterogeneity across the object's surface or emission mechanisms that weren't purely thermal. The ʻOumuamua trace gas orbiter had attempted spectroscopic measurements that produced results so anomalous that initial analysis suspected instrumental malfunction. Repeated calibrations confirmed that the spectrometer was functioning correctly, forcing acknowledgement that the target itself was displaying properties outside the instrument's design assumptions. Most significantly, all three Mars orbiters had detected coordinated brightness variations that suggested controlled orientation, changes rather than chaotic tumbling typical of natural objects. The variations followed patterns that implied active attitude control systems responding to changing solar illumination geometry. The coordination required communication and processing capabilities that pushed far beyond anything achievable through natural gravitational and thermal forces. If confirmed, the observations would provide the first direct evidence of artificial systems operating in our solar system. But confirmation required independent verification through Earth-based telescopes operating at the limits of their capabilities to track an increasingly distant and faint target. The observations needed to distinguish genuine signals from instrumental artifacts while accounting for viewing geometry differences between Mars and Earth. The International Telescope campaign that emerged over the following days represented the largest coordinated effort to study a single interstellar object in history. Observatories across 6 continents contributed data as the global astronomical community attempted to either confirm or refute the extraordinary claims emerging from Mars-based observations. The results, when they began arriving, only deepened the mystery instead of resolving it. The Atacama Large Millimeter Array detected structured radio emissions at frequencies that suggested artificial modulation rather than natural plasma processes. The signals were faint, but clearly artificial, displaying mathematical patterns that couldn't arise from random physical processes. The Very Large Telescope Array in Chile captured infrared spectra showing absorption lines that didn't match any known natural materials, but were consistent with engineered metamaterials designed for specific optical properties. Ground-based radar systems bounced signals off 3I Atlas and received returns that indicated smooth, flat surfaces, rather than the rough, irregular topology typical of comet nuclei. The radar cross-sections were larger than expected and showed geometric features suggestive of constructed rather than naturally accumulated structures. Each measurement added weight to artificial interpretations, while simultaneously raising the stakes for institutional responses. The evidence was accumulating through multiple independent platforms using different methodologies, making systematic error or coordinated misinterpretation increasingly unlikely. The pattern suggested not just unusual natural phenomena, but active artificial systems that were responding to observation attempts in ways that revealed their technological nature. The implications cascaded far beyond astronomical curiosity into territory that no space agency had protocols for handling. The communication challenge became acute as evidence mounted for conclusions that would transform humanity's understanding of its cosmic environment. How do you announce to the world that we've detected confirmed artificial objects from other civilizations without triggering panic, economic disruption, or international conflicts? The institutional paralysis reflected genuine uncertainty about how to manage information that could reshape civilization while maintaining scientific credibility and social stability. The precedents for such announcements simply didn't exist, leaving agencies to improvise responses to situations their founders never anticipated. The leaked fragments of information created a perfect storm of speculation and confirmation that bypassed official control mechanisms entirely. Social media networks, amateur analysis communities, and independent researchers were reconstructing the full picture faster than institutional gatekeepers could manage the narrative. The democratization of information meant that extraordinary discoveries could no longer be contained within professional scientific channels until verification was complete and communication strategies were prepared. The public was witnessing the discovery process in real time, with all its uncertainty, excitement, and institutional fumbling exposed to global scrutiny. The traditional model of scientific communication, where discoveries were announced through peer-reviewed publications after extensive verification, was proving inadequate for managing discoveries that had immediate implications beyond academic research. New frameworks were emerging through necessity rather than design, created by the collision of extraordinary evidence with ordinary bureaucratic processes. The result was unprecedented transparency about how major scientific discoveries actually unfold, complete with false starts, institutional disagreements, and gradual convergence toward conclusions that challenged fundamental assumptions about reality. The 3I Atlas case was becoming a masterclass in how humanity might handle first contact with non-human intelligence, revealing both the strengths and weaknesses of our current institutional frameworks for managing paradigm-shifting information. The lessons learned from this encounter would likely influence how future interstellar visitors are studied, communicated, and integrated into broader cultural understanding of our place in a universe that was proving to be far more complex and populated than we had dared imagine. The leaked information created cascading effects across multiple sectors that revealed just how unprepared human civilization was for this type of discovery. Financial markets experienced what economists would later term the contact correction, as investors struggled to price in technologies that might render entire industries obsolete overnight. Aerospace and defense stocks initially surged on speculation about reverse engineering opportunities, but the gains proved volatile as analysts realized that any civilization capable of interstellar travel would possess capabilities centuries or millennia beyond current human achievement. The technological gap made traditional military and commercial frameworks seem suddenly primitive. Rare earth element prices spiked based on theories that alien technology might require exotic materials, while cryptocurrency markets spawned dozens of contact coins designed for hypothetical interstellar commerce. Most were elaborate scams, but some represented genuine attempts to create communication protocols that might function across species barriers. The religious responses varied dramatically across denominations and faiths. The Vatican issued a carefully worded statement within 48 hours, emphasizing that discovery of intelligence beyond Earth was consistent with Catholic theology. "The universe is vast and full of wonders," Pope Francis declared. "If God has chosen to populate it with other forms of consciousness, this only increases our sense of his infinite creativity." Evangelical Protestant reactions proved more divided. Some leaders embraced the visitors as evidence of God's cosmic scope, while others worried about theological implications that had never been seriously debated. Emergency theological conferences convened in seminaries worldwide as religious scholars grappled with questions that had been purely theoretical until now. Educational systems experienced unprecedented demand for physics, mathematics, and engineering programs as students who had never shown interest in technical subjects suddenly wanted to understand the science behind interstellar communication. Community colleges began offering contact literacy courses, teaching basic concepts needed to participate in humanity's expanding cosmic conversation. The psychological impact manifested in ways that mental health professionals were still learning to recognize. Hotlines reported a 340% increase in calls during the first week after the leaks became public. The conversations followed predictable patterns: existential anxiety about humanity's place in the universe, profound excitement about possibilities ahead, and a peculiar form of cosmic loneliness as people processed the realization that we had never truly been alone. Children's reactions proved particularly telling. Teachers reported that students had begun incorporating space themes into artwork and creative writing with remarkable sophistication. Many children seemed less surprised by the contact than adults, as if they had always assumed the universe contained other intelligences and were merely waiting for grown-ups to figure it out. The media landscape fragmented along predictable lines, as different outlets emphasized either mainstream scientific interpretations or more speculative frameworks. Traditional science journalism struggled to maintain objectivity when covering discoveries that challenged fundamental assumptions about cosmic solitude. Social media platforms faced unprecedented challenges, distinguishing between legitimate updates from verified sources and the inevitable flood of conspiracy theories, hoaxes, and misinterpretation that accompanied such momentous revelations. Bot networks, many apparently state-sponsored, flooded Twitter, Facebook, and TikTok with competing narratives designed to shape public perception. Platform moderators found themselves in the extraordinary position of fact-checking claims about alien intelligence while simultaneously trying to combat misinformation about the visitors' intentions and capabilities. Verification badges appeared on official observatory accounts, creating new categories of trusted sources for cosmic news. The geopolitical dimensions added complexity as different national space programs began positioning themselves for potential technological advantages. China's Beijing Institute of Technology published increasingly detailed analyses claiming artificial characteristics, while European agencies maintained more cautious positions that emphasized natural explanations. The fragmentation of international scientific cooperation, normally insulated from terrestrial political considerations, reflected deeper strategic calculations about information control and technological advantage. If the visitors represented genuine artificial intelligence from another civilization, the nation or alliance that established first communication might gain unprecedented access to advanced knowledge. Private aerospace companies reported surge in investment inquiries as venture capitalists attempted to position themselves for potential technological windfalls. SpaceX, Blue Origin, and other commercial space firms saw their valuations fluctuate wildly as markets tried to assess which companies might benefit from reverse engineering opportunities. The speculation proved premature, since any technology capable of interstellar travel would likely render current propulsion and materials science obsolete. But the investment patterns revealed underlying assumptions about how transformative contact might prove for human technological development. Urban planning discussions began incorporating speculative elements about how cities might need to evolve for a species that knew it wasn't alone in the universe. Architecture schools offered workshops on designing for post-contact societies, though the practical applications remained entirely theoretical. The cultural impact extended to unexpected domains. Museums organized emergency exhibitions featuring space-themed works. New musical compositions appeared almost daily, many incorporating prime number rhythms or the actual radio frequencies detected from 3i Atlas. Visual artists created installations using the hydrogen line frequency as an organizing principle. Night sky photography exploded in popularity as amateur astronomers invested in telephoto lenses and tracking mounts, hoping to capture images of interstellar visitors. The photos themselves were unremarkable, distant points of light indistinguishable from stars, but the act of documentation seemed to satisfy deep human needs to witness and share historic moments. Dating apps added views on extraterrestrial contact to their matching algorithms. Marriage proposals reportedly included references to the cosmic perspective. Pet adoption rates spiked, possibly reflecting desires for companionship during uncertain times when humanity's place in the universe suddenly seemed far more complex. The temporal perspective shift proved perhaps most significant. People began thinking in longer timescales, considering decisions in contexts of cosmic history rather than quarterly earnings or election cycles. The realization that we might be part of a larger community of minds scattered across the galaxy was slowly transforming how humans thought about progress, achievement, and responsibility. Corporate marketing adapted with remarkable speed as advertisers attempted to capitalize on cosmic consciousness. Car commercials featured families driving to dark locations for better sky viewing. Smartphone manufacturers emphasized their cameras' low-light capabilities for astrophotography. Coffee companies marketed contact blends for those long nights of sky watching. The insurance industry faced entirely new categories of risk assessment as the possibility of interference, intentional or accidental, from advanced alien technology created liability scenarios that had never been contemplated. Satellite communication companies saw dramatic shifts in their coverage rates as insurers struggled to price policies for systems that might encounter technologies beyond human understanding. The agricultural sector experienced unexpected impacts as some farmers reported changes in livestock behavior that coincided with the leaked revelations. Veterinarians couldn't establish causal connections, but the correlations were strong enough to generate research proposals for studying how cosmic awareness might affect animal psychology. Manufacturing industries began receiving inquiries about producing components for hypothetical communication arrays, despite the fact that no official construction projects had been announced. The speculative demand reflected public assumption that humanity would inevitably attempt to establish formal contact protocols. The entertainment industry struggled to adapt content strategies when reality began outpacing science fiction. Movie studios found themselves competing with actual cosmic mysteries that were more compelling than most fictional narratives. Streaming platforms reported surge in documentaries about space exploration and astrobiology. Book publishers rushed to commission titles about interstellar communication, cosmic consciousness, and humanity's place in galactic civilization. Academic presses found themselves fielding proposals for textbooks about subjects that hadn't existed as formal disciplines just weeks earlier. The legal profession began developing frameworks for extraterrestrial intellectual property, interspecies communication rights, and cosmic environmental protection. Law schools offered seminars on astro-legal studies, though the practical applications remained entirely theoretical until formal contact protocols were established. The medical community started documenting psychological and physiological responses to cosmic awareness, creating new diagnostic categories for adjustment disorders related to paradigm-shifting revelations about universal consciousness. The research would prove valuable for managing future contact scenarios that might prove even more psychologically challenging. The scientific publishing industry experienced unprecedented demand for rapid peer review of papers related to interstellar visitor characterization. Journal editorial boards struggled to maintain quality standards while accommodating urgent research that addressed questions of extraordinary significance. The Patent Office received hundreds of applications for devices designed to communicate with extraterrestrial intelligence, despite the fact that no verified contact protocols had been established. The applications revealed fascinating insights into how different inventors conceptualize the technical challenges of interspecies communication. Professional conferences across multiple disciplines began incorporating cosmic perspective sessions as researchers in fields ranging from anthropology to psychology attempted to understand how their disciplines might need to evolve in response to confirmed evidence of non-human intelligence. The transformation was happening in real time as human civilization began adapting to possibilities that had been purely theoretical just days earlier. Every sector of society was being forced to confront questions that had never required practical answers, creating a period of unprecedented intellectual and cultural ferment. The speed of adaptation revealed both human resilience and the fragility of assumptions that had seemed unshakable just weeks before the first leaked images appeared online. The 3i Atlas encounter was becoming a stress test for human institutions, psychology, and adaptive capacity on scales that no previous discovery had approached. The most profound change was perhaps the simplest. Millions of people had begun looking up at the night sky with new awareness that the points of light they saw might harbor intelligences asking the same questions, facing similar challenges, and reaching toward the same distant possibilities that had inspired human dreams since we first wondered what lay beyond our small world. The conversations that emerged from this shared cosmic consciousness were reshaping everything from family dinner discussions to international diplomacy. Of to think humanity was beginning itself not as an isolated species on a lonely planet, but as participants in a larger community of minds whose true scope and nature we were only beginning to glimpse. The institutional frameworks designed to manage this transformation were proving inadequate for the speed and complexity of changes that cosmic awareness was triggering. New approaches to governance, communication, and international cooperation were emerging through necessity rather than design, created by the collision of extraordinary discoveries with ordinary human social structures. The precedents being established during these crucial weeks would likely determine how humanity navigated not just this encounter, but whatever other revelations about cosmic intelligence might emerge as our detection capabilities continued improving and our understanding of interstellar phenomena deepened. The 3i Atlas case was becoming far more than an astronomical curiosity. It was evolving into a comprehensive test of human adaptability, institutional flexibility, and collective wisdom in confronting realities that exceeded our most ambitious science fiction, while demanding practical responses that would shape our species' cosmic future for generations to come. The cascade of revelations continued to accelerate. ASD analysis leaked more fragments of classified through increasingly creative channels. A graduate student at MIT accidentally forwarded an email thread to a public mailing list that contained references to Project Looking Glass, apparently NASA's internal codename for the comprehensive 3i Atlas investigation. The email fragments revealed coordination between multiple government agencies that extended far beyond typical space science collaborations. The Department of Defense had quietly assigned analysts to review the Mars observations. The National Security Agency was monitoring global communications for any signals that might correlate with 3i Atlas's position. Even the Treasury Department had economists modeling potential impacts of disruptive technology acquisition scenarios. The scope of institutional involvement suggested that whatever the Mars platforms had detected was being treated as a matter of national security rather than academic curiosity. This level of government coordination typically occurred only for events with immediate strategic implications for national defense or economic stability. Within academic circles, whispered conversations revealed that senior researchers at major universities had been approached by government representatives asking pointed questions about theoretical frameworks for distinguishing natural from artificial phenomena in space-based observations. The inquiries were framed as hypothetical research problems, but the timing and specificity made their connection to 3i Atlas obvious. Professional astronomical societies found themselves in unprecedented positions as members demanded transparency about institutional knowledge of the Mars observations, while leadership maintained that no official information had been shared beyond what appeared in public archives. The tension reflected deeper fractures between institutional loyalty and scientific transparency that were becoming impossible to ignore. The breakthrough came from an unexpected source entirely. A ham radio operator in Finland detected structured transmissions on frequencies that corresponded precisely to 3i Atlas's predicted position as calculated from published orbital elements. The signals weren't random noise or natural plasma emissions. They displayed mathematical patterns that could only arise from intentional modulation. The Finnish detection sparked a global effort among amateur radio enthusiasts to verify and characterize the signals. Within hours, operators across multiple continents confirmed the transmissions and began collaborative analysis through online forums that bypassed traditional scientific publication channels entirely. The signal structure was elegant in its simplicity. Groups of pulses corresponding to prime numbers, transmitted in sequences that suggested mathematical sophistication, far beyond what natural processes could produce. The pattern was unmistakably artificial and clearly intended to be recognized as such by any civilization capable of detecting it. But the most unsettling aspect was the signal's temporal behavior. The transmissions weren't constant broadcasts, but appeared to respond to observation attempts. When multiple radio telescopes pointed toward 3i Atlas simultaneously, the signal strength increased. When observations ceased, the transmissions faded to barely detectable levels. This responsive behavior implied real-time monitoring of Earth's radio telescope activities and active modulation of transmission power based on human observation patterns. The level of situational awareness required for such responses suggested intelligence that was not only present, but actively engaged with our attempts to study it. The professional radio astronomy community could no longer ignore what amateur operators had discovered. The Arecibo Observatory's successor facility in Puerto Rico conducted emergency observations that confirmed both the signal's artificial nature and their responsive characteristics. The Very Large Array in New Mexico contributed additional data showing that the transmissions originated from a compact source consistent with 3I Atlas's position, rather than from distributed background emissions. The signals were definitely coming from the object itself, not from some unrelated cosmic phenomenon that happened to appear at the same coordinates. European radio telescopes added their own confirmations, creating a global data set that left no doubt about the signal's reality or their artificial origin. The evidence was now too robust and widely distributed to suppress through institutional channels or dismiss as observational error. The responsive nature of the transmissions created an immediate ethical dilemma that no existing protocols addressed. If 3I Atlas was actively monitoring our observation attempts and modulating its signals accordingly, then every radio telescope pointed in its direction constituted a form of communication attempt, whether intended as such or not. The implications forced emergency meetings at the highest levels of multiple space agencies as officials grappled with questions that had been purely theoretical until now. How do you study an object that's studying you back? What are the diplomatic implications of observations that might be interpreted as hostile surveillance by an intelligence of unknown capabilities and intentions? The United Nations Office for Outer Space Affairs convened emergency sessions to discuss protocols for managing what appeared to be humanity's first confirmed communication with non-human intelligence. The existing frameworks for international space cooperation had never anticipated scenarios where space objects might possess their own agency and intentionality. The timeline pressure added urgency to these deliberations. 3I Atlas was continuing its hyperbolic trajectory away from optimal communication range. Each day of institutional debate was a day of lost opportunity for establishing meaningful dialogue, while conditions remained favorable for signal detection and transmission. Amateur radio networks had already begun attempting structured responses to the prime number sequences, broadcasting mathematical progressions and basic physical constants toward 3I Atlas's predicted position. The responses were uncoordinated and potentially contradictory, creating cacophony rather than coherent communication. The risk was that humanity's first conversation with non-human intelligence might be characterized by confusion and mixed messages rather than the careful, coordinated approach that such a momentous event deserved. Professional SETI researchers who had spent decades developing protocols for first contact found themselves sidelined by the rapid pace of events and the distributed nature of the discovery process. The signals themselves began evolving in response to the various transmission attempts from Earth. The simple prime number sequences gave way to more complex mathematical progressions that seemed designed to test human understanding of advanced concepts in number theory and physics. When amateur operators broadcast the value of pi to 15 decimal places, 3I Atlas responded with mathematical constants that human science had discovered but never transmitted into space. The golden ratio, Euler's number, and the fine structure constant appeared in the response sequences with precision that exceeded published human measurements. The demonstration of knowledge about physical constants that humanity had never broadcast suggested either remarkable coincidence or intelligence that had been monitoring human scientific development for far longer than the few months since 3I Atlas's discovery. The implications for how long we might have been under observation were staggering. The mathematical sophistication of the responses also indicated capabilities that exceeded human achievement in certain domains. Some of the number sequences corresponded to solutions of problems in advanced mathematics that human researchers had been working on for decades without success. The visitor was demonstrating not just intelligence, but intelligence that surpassed human understanding in specific technical areas. This revelation forced a fundamental reassessment of humanity's position in any potential cosmic hierarchy. The comfortable assumption that human intelligence represented some kind of pinnacle of cosmic achievement was being systematically demolished by each new mathematical demonstration from ʻOumuamua. The psychological impact on researchers directly involved in the communication attempts was profound. Several mathematicians reported experiencing what could only be described as intellectual vertigo as they confronted evidence of minds that operated at levels they could barely comprehend while remaining accessible enough for basic communication. The philosophical implications rippled through academic disciplines far removed from astronomy and mathematics. If intelligence existed at scales that dwarfed human achievement, what did that mean for concepts of consciousness, creativity, and purpose that had been developed around human-centric assumptions? Religious institutions found themselves confronting questions about divine creation and cosmic purpose that theology had never seriously addressed. If God had created multiple forms of intelligence throughout the universe, did they all share common purposes? Or were there cosmic missions that exceeded human understanding entirely? The educational system struggled to incorporate these revelations into curricula that had been designed around the assumption of human uniqueness. How do you teach children about their place in a universe that might contain intelligences as far beyond human capability as humans were beyond insects? The economic implications began manifesting in ways that revealed deep assumptions about technological progress and competitive advantage. If ʻOumuamua represented access to scientific knowledge that exceeded human discovery by centuries or millennia, traditional models of research and development became obsolete overnight. Industries based on gradual technological advancement faced existential questions about their relevance in a world where paradigm-shifting discoveries might emerge through contact with advanced cosmic civilizations. The patent system, intellectual property law, and innovation economics all required fundamental reconsideration. The military establishments of major nations began classified assessments of scenarios where potential adversaries might gain exclusive access to advanced alien knowledge. The strategic implications of asymmetric technological advantage derived from extraterrestrial sources had never been seriously analyzed because the possibility had seemed too remote to warrant planning. Defense analysts found themselves developing contingency plans for situations that exceeded the scope of traditional military planning. How do you maintain national security when the technological landscape might be revolutionized by discoveries that transcend terrestrial geopolitical boundaries? The international cooperation frameworks that had evolved for managing space exploration and scientific research proved inadequate for handling discoveries with immediate strategic implications for national power and economic competitiveness. New diplomatic approaches were needed for managing information that could reshape civilization while preventing it from becoming a source of international conflict. The communication protocols that emerged from these urgent deliberations reflected compromises between scientific transparency and strategic caution that satisfied no one completely but provided frameworks for moving forward despite institutional disagreements about optimal approaches. The decision was made to establish a coordinated international response team that would manage future communication attempts with ʻOumuamua, while ensuring that any knowledge gained would be shared equitably among participating nations. The framework borrowed heavily from existing models for international scientific collaboration, while adding security protocols that reflected the strategic sensitivities involved. The response team included representatives from major space agencies, leading universities, and government defense establishments. The composition reflected recognition that contact with advanced extraterrestrial intelligence was simultaneously a scientific opportunity and a national security challenge that required expertise from multiple domains. The team's first priority was establishing communication protocols that would present humanity as unified and rational, rather than fragmented and chaotic. The amateur radio responses that had characterized the initial contact attempts were gradually coordinated into coherent messaging that reflected careful consideration of how to represent human civilization to cosmic intelligence. The content of these coordinated messages became subjects of intense debate as experts from linguistics, anthropology, and philosophy contributed perspectives on how to communicate essential information about human nature, achievements, and aspirations in ways that might be comprehensible to non-human minds. The mathematical language that had emerged organically during the initial contact attempts provided a foundation for more complex communication, but expanding beyond basic arithmetic required assumptions about shared conceptual frameworks that might not exist between species that had evolved in completely different environments. The challenge was compounded by time constraints imposed by three ʻAumuamua continuing trajectory away from Earth. Each day of communication delay reduced signal strength and increased the risk that the conversation might be terminated by purely physical limitations rather than by conscious choice on either side. The pressure to maximize information exchange during the remaining contact window forced difficult decisions about communication priorities. Should humanity focus on learning about three ʻAumuamua origins and capabilities, or on demonstrating human achievements and potential for cosmic citizenship? The debate reflected deeper questions about what humanity most needed to understand about its cosmic environment and what messages would best represent human civilization to intelligences that might be evaluating our species' readiness for broader cosmic community membership. The responses from three ʻAumuamua suggested that these questions were not merely academic. The mathematical demonstrations appeared designed to test human cognitive capabilities and scientific understanding, rather than simply acknowledging communication attempts. The visitor seemed to be conducting its own assessment of human intelligence and technological development. This realization transformed the communication attempts from simple message exchange into something resembling a cosmic entrance examination, where humanity's responses might determine our future relationship with advanced extraterrestrial civilizations. The stakes could hardly have been higher, or the evaluation criteria less clear. The mathematical complexity of three ʻAumuamua transmissions continued escalating, as if the intelligence behind them was systematically probing the limits of human understanding. Problems in advanced physics and mathematics that had puzzled human researchers for decades appeared as challenges embedded within the communication sequences. Some responses seemed designed to teach rather than test, providing solutions to human scientific problems, along with mathematical proofs that demonstrated methods for deriving those solutions independently. The pedagogical approach suggested intelligence that was not merely superior, but actively interested in fostering human intellectual development. This mentoring aspect of the communication created hope that contact with three ʻAumuamua might prove beneficial for human scientific advancement, while simultaneously raising concerns about dependency relationships that might develop if humanity became reliant on extraterrestrial guidance for technological progress. The balance between learning from advanced intelligence and maintaining human intellectual autonomy became a central theme in discussions about how to structure ongoing communication attempts. The goal was to maximize knowledge transfer while preserving human agency and creative independence. The technical challenges of maintaining communication as three ʻAumuamua moved beyond optimal range forced innovations in signal processing and transmission power that pushed human radio technology to its limits. The effort required international cooperation on scales that had never been achieved for purely scientific purposes. The infrastructure investments needed to sustain long-range communication with interstellar objects created new categories of technological development that blurred traditional boundaries between scientific research and national defense capabilities. The dual-use nature of interstellar communication technology added complexity to international cooperation agreements. The precedents being established during these crucial weeks would likely influence how humanity approached future interstellar encounters and managed the technological capabilities needed for sustained cosmic communication. The institutional frameworks developed for the 3I Atlas case would shape interstellar diplomacy for generations. The broader cultural impact continued rippling through every aspect of human society as the reality of confirmed extraterrestrial intelligence became impossible to ignore or dismiss. The conversation that had begun with astronomical observations had evolved into comprehensive re-evaluation of humanity's cosmic role and future possibilities. The transformation was occurring in real time as institutions, individuals, and entire civilizations adapted to knowledge that challenged fundamental assumptions about consciousness, intelligence, and cosmic solitude that had shaped human culture for millennia. The 3I Atlas encounter was becoming humanity's first comprehensive test of its readiness to join a larger cosmic community, and the results would determine not just our immediate future, but our species' trajectory across timescales that exceeded any previous human planning horizons. The mathematical dialogues between Earth and 3I Atlas had established something unprecedented in human history, a conversation across the cosmic void that operated in the universal language of numbers and physical constants. But as October moved toward November and away from optimal communication range, the transmissions began displaying. The object continued its hyperbolic journey, characteristics that pushed beyond academic exchange into territory that challenged every assumption about the visitor's true nature. The pattern recognition algorithms that amateur radio operators had developed to decode the mathematical sequences started detecting embedded structures within the number patterns themselves. Hidden beneath the prime progressions and physical constants were what could only be described as instructions, not abstract mathematical concepts, but practical engineering specifications encoded in binary mathematics that any technological civilization would recognize. Dr. Sarah Chen at MIT's Lincoln Laboratory was among the first to recognize what they were seeing. The sequences weren't just demonstrating mathematical knowledge, they were blueprints. Detailed technical drawings expressed in numerical form that described construction methodologies for devices whose purpose was initially unclear, but whose sophistication was immediately obvious. The specifications included precise measurements, material properties, and assembly procedures for what appeared to be some kind of communication array. The design was elegant in its simplicity, using technologies that 21st century Earth could reasonably manufacture, while incorporating principles that human engineering had never developed independently. The power requirements were modest by industrial standards. The component materials were exotic, but available through existing supply chains. Most remarkably, the design included optimization parameters specifically calibrated for Earth's rotation period, magnetic field characteristics, and atmospheric composition. This wasn't a generic template that might work for any technological civilization. It was a custom design created specifically for humanity's current technological capabilities and planetary environment. The level of detailed knowledge about Earth's physical properties implied observation and analysis that had been conducted over extended periods with precision that exceeded most human scientific measurements. The implications sent shockwaves through the international response team that had been coordinating Earth's communication efforts. If 3I Atlas possessed such detailed knowledge about human technological capabilities and planetary characteristics, how long had it been studying us? And what did that surveillance suggest about the visitor's ultimate intentions? The engineering specifications continued arriving in daily transmission sequences, each one building upon previous designs to create an integrated system whose full purpose was gradually becoming clear. The device being described was an interstellar communication beacon designed to interface with what appeared to be a galaxy-wide network of similar installations. The technical documentation included network protocols, frequency allocation schemes, and data formatting standards that implied membership in an established communication infrastructure spanning multiple star systems. Humanity wasn't being invited to establish first contact. We were being offered the opportunity to join an existing cosmic internet that had been operating for an unknown period. The revelation transformed every assumption about our cosmic isolation. The universe wasn't empty space, punctuated by occasional technological civilizations, struggling to establish contact across vast distances. It was a connected community where information flowed routinely between star systems through infrastructure that made interstellar communication as reliable as terrestrial internet connections. The beacon specifications included explicit warnings about maintaining electromagnetic quiet near biological surfaces, suggestions that powerful transmitters should be positioned away from inhabited worlds, and protocols for preventing interference with naturally occurring radio astronomy phenomena. The safety guidelines demonstrated sophisticated understanding of how advanced communication technology might impact planetary ecosystems. These environmental considerations suggested that whoever was behind the transmissions had extensive experience with biological worlds and the delicate balance required to maintain technological civilization without destroying the natural systems that supported it. The guidance read like lessons learned from managing similar integration processes across multiple planetary civilizations. The construction timeline implied urgency that was initially puzzling. The beacon could theoretically be assembled and operational within 18 months if humanity committed appropriate resources and international coordination. But why the emphasis on rapid deployment? What deadline was driving this accelerated schedule? The answer came through analysis of the network protocols embedded within the technical specifications. The communication infrastructure operated on synchronized timing cycles that aligned with astronomical phenomena occurring on predictable schedules. Galactic rotation, stellar proper motion, and gravitational lensing effects all influenced optimal transmission windows between different regions of the galaxy. Earth's next optimal integration window would open in approximately 2 years and then not recur for several decades. If humanity wanted to join the galactic communication network efficiently, the beacon needed to be operational before this astronomical alignment shifted beyond favorable parameters. The timing constraint added pressure to international deliberations about whether to proceed with construction. The decision couldn't be delayed indefinitely while diplomatic and technical details were resolved. Either humanity committed to building the beacon within the specified timeline, or the opportunity would be delayed by decades. The technical challenges were substantial but manageable within Earth's current industrial capabilities. The more difficult obstacles were political and social. How do you coordinate a planetary construction project when no existing institution has authority to speak for all of humanity? What happens when different nations disagree about whether joining a galactic communication network serves their interests? The beacon specifications included provisions for distributed construction, where different components could be manufactured in multiple locations and then assembled at a final integration site. This approach would allow international participation while maintaining some degree of redundancy if political disagreements disrupted cooperation. The location requirements were specific and non-negotiable. The beacon needed to be positioned at precise geographical coordinates that optimize signal propagation through Earth's magnetic field, while minimizing interference with existing radio astronomy installations. Several potential sites met the technical criteria, but they were distributed across different national territories. The site selection process became a complex negotiation involving sovereignty issues, resource commitments, and strategic considerations about which nations would host infrastructure that might become humanity's primary interface with galactic civilization. The discussions revealed deep tensions between national interests and species-wide cooperation. Meanwhile, 3i Atlas continued broadcasting increasingly detailed technical specifications that addressed every aspect of beacon construction from foundation engineering to software protocols. The completeness of the documentation suggested that this integration process had been refined through repetition across multiple civilizations. The visitor wasn't improvising solutions to unique challenges posed by human technology and planetary environment. It was implementing a standardized procedure that had been developed through extensive experience with similar integration projects. Humanity was being processed through a well-established protocol for inducting new members into galactic communication networks. This realization was simultaneously reassuring and unsettling. Reassuring because it suggested that the process had been successful enough to be worth standardizing across multiple civilizations. Unsettling because it implied that humanity's uniqueness was less significant than we might have hoped in cosmic terms. The software components of the beacon design included artificial intelligence frameworks that would manage network protocols, translate between different communication standards, and optimize transmission parameters based on real-time astronomical conditions. The AI specifications were more advanced than anything in human computer science, but remained comprehensible to researchers familiar with machine learning principles. The question that began this investigation was simple. What did those new images from Mars reveal about 3I Atlas? The answer, as we've discovered, is far more complex and unsettling than anyone anticipated. We started with a blue smudge in a leaked image that contradicted every established measurement of this interstellar visitor. We followed that thread through layers of institutional silence, statistical impossibilities, and coordinated responses that suggest we're witnessing something unprecedented in human history. The evidence speaks for itself. Mathematical transmissions responding to our observations. Engineering blueprints designed specifically for Earth's technological capabilities. Network protocols for joining a galactic communication infrastructure that's been operating while humanity thought it was alone in the cosmos. Whether 3I Atlas represents natural phenomena pushing the boundaries of physics or our first confirmed contact with cosmic intelligence, one thing is certain. We're living through a moment that will define our species' future among the stars. The universe has revealed itself to be far stranger, far more connected, and far more populated than we ever dared imagine. The blue smudge from Mars was just the beginning.